2 minutes past the scheduled time. So let's start officially. So,
Okay.
friends, welcome to session 9 of the masterclass in audio. Um we are really privileged to have Ron Sauro and John Brandt with us. The formal introductions will happen by my friend and dear friend and colleague Mazban Irani. All I can say is that this is a session that we are all anticipating with much bated breath, in a sense, because Ron is a ex-NASA scientist and highly acclaimed acoustician, musician, wears many hats, and someone who has very, very interesting perspectives on audio and acoustics. But he will choose to talk on acoustics more today. And we also have John Brandt, his a very good friend and colleague in the industry, who is a very famous person who has recorded who has designed more than probably 900 to 1,000 recording studios across the world, and a highly acclaimed designer. So over to you, Masban, for the introductions and taking over the session.
Thank you, Karthik. Welcome, friends. Like Karthik said, today is really a session that we've all been looking forward to. We have two colossus in our field who are going to talk to us about the science behind what we all love and want to do for the rest of our lives. That's audio and acoustics. So I'll start by introducing you to our first expert, Ron Sauro. As a young boy in a high school physics class, he built an atom smasher in 1962. That's an electron accelerator, for those who don't know, as a science fair project. And even after he built it, he was told that he does not have the discipline needed to be a scientist. And in the same year, in 1962, he survived a small aircraft plane crash during search and rescue operations of the CAP. And in 1963, he and his friends, being a musician, he recorded a top 10 rock and roll record, which sold more than 1 million copies. He then volunteered to join the Air Force in 1964 and was shipped off to Vietnam, where he was there on the ground during the Gulf of Tonkin Day. And like he just mentioned a little earlier, a sniper shot his friends and got him in the chin. And he survived that as well. So, and when he came back after the service, he survived 2 fatal car crashes. So Ron is definitely a survivor, and we are so glad that he survived, because after his discharge from the Air Force, he went to work as a technician for NASA at Ames Research Center, California in 1968. And because of the shortages of scientists and engineers, he was selected to attend Stanford University and a special program designed by NASA to develop the needed scientists. So this program was, a single year, highly compressed placement program, and which got him the certification of engineering scientist with basic degrees in physics, electronics, and mechanical engineering. So a few accomplishments of Ron. He was the first gentleman to invent the metal detector, which is used in all airports today. That was a result of the first airline hijacking by D.B. Cooper. He also then invents the test equipment needed to measure the magnetic signature of miniature atomic reactors on space probes. So he specializes in the field of micro or miniature magnetics. And he designed and invented the first multi-channel solid-state magnetometer and multi-position magnetometer mounting system. And he used a high-speed data acquisition system, designed it using cassette storage medium, which is, I think, brilliant. He's also designed multiple magnetic experiments for the Apollo, Viking, Pioneer, Voyager, and the Cassini program. So, Ron, we really doff our hat off to you for helping us find new worlds. So he again avoids another fatal collision on his flying laboratory in a Navy aircraft, which almost killed him. He avoided that because he was late to work due to traffic. And then after that, he realized that this is not the place I've got to be. So he left NASA and spent many years as a traveling professional musician and working in many other types of jobs. Then Ron decided that he got tired of living on the road. He went and opened an electronic repair facility for musical instruments. And then he started contracting and designing sound systems. And as a part of that, he got involved with the development of ease with Wolfgang Anhert of Berlin. And so this is something that we've all used, we all have seen. And he has, in fact, developed and designed the systems that go behind the GLL files, how you measure and put that data into a GLL file, which is used by EASE. So as part of the design process using EASE, Ron became frustrated with the inability of making better predictions of project room acoustics. And after researching the simulation programs, he realized that the theory was sound, but the databases had bad data. And that was incomplete data and data which was full of errors. So then he decided to convert a 1960 invention which he used in the area of acoustics and audio, but he needed a lab to set it up. And that's when NWAA Labs was born. The lab was funded using his and his wife's retirement funds, and of course with the help of many friends. And this facility is where all materials, a lot of materials, loudspeakers, all things that go into audio are tested even today. So Ron, welcome to the session. We are really honored to be in your company today. Second speaker and expert is none other than John Henry Brandt III, who was born in Coalinga, California, but raised in Texas. And he began his career in a music business after high school when he joined a touring band as a roadie. So that's absolutely from the ground up he's worked. And then he worked his way up to being an FOH engineer in 2 years. And then he moved to Paris in 1974 and worked with the next ex-Fleetwood Mac member, Jeremy Spencer, who's still his friend today. John toured Europe until 1976, after which he moved to the UK and he began his studies in electronics and acoustics in 1976. And for the next 4 years, he worked many different studios and ran sound. I mean, he operated sound at many clubs from London to Glasgow. In 1980, he moved back to the States, where he joined the Army for 3 years. So that's what they have in common. Both are Army gents here today. And he left in Air Force. Okay. I know you guys. Army and Air Force are loggerheads. So he left in 1983 with an honorable discharge and an Army Commendation Medal. After the year he left the Army, he built his own studio in Texas and continued to provide FOH services for many artists, including Tanya Tucker, David Thomas, and Little Joe La Familia. In 1986, he was hired by Bob Millsap as the chief engineer at Ironside Studios in Branson. And in 1989, John moved to Nashville, the capital of country music, to further his career, where he worked with many notable producers and engineers in Nashville with electronics design and acoustic consulting. So John has spent his life making the art of recording music easy for artists, producers, and engineers. And he's actually got outstanding results because basically for his passion for the recording arts. He's got a brilliant and creative mind, and his expertise is in designing recording studios, listening spaces, media rooms, and even home theater rooms, and more in the small room acoustics part of it. I'm sure he can manage large room acoustics as well. In fact, he was telling us that he has been shortlisted to consult on a very large project in Saudi Arabia. And he's been contracted from 3 different architects and also. This is a guy who's so much in demand. So, John, thank you so much for being with us. We really are, again, honored to be in your presence as well. And let's start this session off today with Ron. And Ron, you can start talking about, your development of EASE, the NWAA labs, and what testing means to the industry and why is it so important. I mean, we like John was commenting that we always expect one result, but when you actually analyze it and go into testing, you figure out that, oh my God, it's completely different.
Yes. Well, thank you very much. It's one of these things where NASA kind of informed how I do things because there you have to be a scientist, and the only thing that speaks is real results. It has nothing to do with theory. Theory is nice, but until you can prove the theory, it is just a theory and it's just a thought. So that's one of the things we had to do when we put things on board these spacecraft is think 40 years in advance and figure out where we're going to be. and what we were looking for, so we could go on with the next steps each time. So I'm always watching what's going on out there with SpaceX and all these other things going on, because it's a great thing that's going on, where I'm finally able to see it happen before I die. So I'm kind of excited. But by the same token, what I found was I put my reputation on the line every time I did a large venue like a stadium or an opera house or whatever. And my reputation got trashed a number of times because the results that I got were not with the range of what I predicted. And it was like, okay, so then I started talking with Wolfgang Honert and the people at Ease and other companies as well. And we all talked about, what it takes to do a prediction. And there are lots of formulas that have gotten out there from Rayleigh and all the other people from the 1700s all the way until now that have been really, really good if you have solid data behind them. So, it's kind of like, if you have a boat and you have a great boat and it's floating, but you have a hole in the bottom of it because somebody pulled the plug out, the boat's going to sink eventually. And that's what happens in the field of acoustics. We have lots and lots of holes in our data because the ability to measure it is restricted by space. Okay, so if you don't have a large enough space to measure something, you can't expect to measure it in the frequency range where a lot of us work. And up until the last few years, everybody had been worried about what the sound occurs with the human voice. So we're worried about intelligibility. We're worried about how intelligible something is. And the problem with that is that's a very restricted frequency range of around 250 hertz to roughly about 4,000 hertz. And that's very limited, and that's fine. As long as that's all we're worried about, then all the stuff that we've been testing for all these years is fine, because that's a very limited area. But the reverberation rooms that are in the world out there all have one thing in common. They're all too small. And what you have here is a group of people who have decided that it's this way, it's been this way since over 100 years now. The first reverberation rooms were built about the year 1905, something like that. And they were about 180 to 200 cubic meters. And everything built since that time has been about the same size, which means if you look at the Schroeder drop-off frequency of a room, these rooms, because of their volume and their surface area, have a restriction of about 200 hertz. So anything below 200 hertz is at best a guess. And it's kind of like, well, if it's doing this and we see a curve of absorption going up, we're going to assume that it's going to continue that curve if it's beyond where we can measure. The problem is 99% of the time, that's not true. And that's one of the reasons why I was asked to open laboratory many years ago. And I told Wolfgang Honert that, in spite of having my background, if you don't have the right tools, then it's a waste of time and energy to duplicate what everybody else is already doing. So I ended up waiting until I had the opportunity to find this place that I'm in right now, which was basically a nuclear power plant that was in the process of being built in the 1970s. And it was put into it was about 2 weeks from being turned on. It was going to be the largest reactor in the world that had a capability of approximately about 2.5 gigawatts of power. It was a big place, okay? And they put it into mothballs on the grounds that they were going to, because of the 3 Mile Island, they were going to put it in mothballs for about a year, then go back and start construction again. Well, that never happened. And after 40 years, the county who was keeping track of it decided it was costing $1 million a year to keep it mothballed, and they just couldn't afford to keep on doing that for years. So they basically abandoned it and gave it to the county. And the county, like, we don't want it. We had no use for it. So it was one of these things where I was passing by, and I remember watching it being built, and I was looking for a mountain to put my new laboratory in. And this was on the side of a mountain, and I thought, well, we dig it out, we'll put a building inside of it and cover it up again. And then my wife said, well, have you ever thought about just using the reactor building? And I'm going, well, yeah, but I think it's probably not going to be usable. So I went up and looked at it. They showed it to me, and I looked at it and thought, well, yeah, it's a possibility with some modifications. I could probably do that. So I ended up moving in to prove a proof of concept. So we ended up modifying this building and building the entire thing. And what was interesting is I contacted the contractors, and they all told me it can't be built because you're asking too much accuracy in construction. So the idea here was to build a room that was the largest in the world, and it had to be accurately built corner to corner, corner to corner, to a 1/16 of an inch. Yeah, and they all said, can't do that. There's no way we can do that. So what I found a long time ago is if you hire people and teach them how to do it and they don't know it can't be done, be surprised what you can do. So I hired 2 people that had nothing to do with construction. I showed them how to do it because I was a general contractor at one time. And they built it. And what was really funny is we signed the contracts to build this place in May of 2010. We started construction at the end of May in 2010, and we were finished and operational by September of 2010. So yeah, it was only 3 months to build this entire place. And it was all done with myself, my wife, and these 2 guys. And that was it. So it was, you know, I got told very simply, you can't build a place like that. And we're going, well, you know, I think John knows me well enough to know that when people tell me I can't do something, I will do it just to spite.
Just to spite them. Yeah, I'm the
Yep.
same.
So so we ended up opening up in October of 2010, and my first client was a company called Purdue Acoustics, and you know, and they're all saying, what can you do? Well, we didn't know for sure what we could do. We just knew we could go lower frequency than other people could. But the facts were that when we actually went through and started checking it out, seeing what could be done with repeatability measurements, we found out we could go down to about 20 to 25 hertz because our place is that big. So we felt pretty comfortable, and we've shown over the years now that we can measure things at 20, 25 hertz with the same accuracy as everybody can do at about 200 hertz. You know, so we're pushing hard now to push the limits of acoustics down into the range of 25 hertz so that we can start working, because the majority of the environmental problems we have with noise is mostly happening in the low frequencies, in the infra low frequencies, with what do you call it, turbines, wind turbines. If you have wind turbines, they vibrate at around 10 to 15 hertz, and they go down into the earth and they transmit all around them for about 2 or 3 5 miles and go into the homes, and then they cause the walls inside of people's homes to also vibrate. And this causes all kinds of health problems. They've started finding out that it's causing lots of people having nerve problems. It deadens the nerves in some cases. It's caused heart problems and all kinds of stuff. So this is one of the reasons why you're starting to see countries that stepped out in advance for these wind turbines. They're starting to tear them down because of the health problems they're being induced. And so that's one of the things we got involved in, was testing for those infrasonics. And you know, and we've been working with University of Washington in the applied physics lab, and their specialty is bioacoustics. So we're seeing how it affects the body, how it affects the mind, and stuff like that. And this is one of the biggest areas of research we're doing now. So, you know, that's been part of this whole thing, is trying to get down to the point where we can get quiet enough to see what it does to the body and what it does to other things, and how do we build buildings, and how do we construct facilities that are not going to hurt us. And that's what I've been doing now for the last 13 years. And so the other thing that's happened is there was a move about 13 years ago by the ISO to put together a measuring system for measuring what was called scattering. And scattering was kind of invented because the absorption coefficient didn't quite work the way that we thought which it should. So if you measure something, you would get answers that were in excess of 1. And according to the mathematical construct here, as a coefficient, you can't exceed 1. The coefficient is a number always between 0 and 1. But the answers were beyond that. And the answer that I got from people was, well, this is something that happens in measuring, and it occurs because of, quote, edge effect. And this is the magic name, edge effect, okay? And when you ask people what edge effect was, you never, ever got an answer. It was always like, well, it's something we don't understand, but it happens because of the edges. And we're looking at it going, what happens? That's my question. What happens? And they go, well, we don't really understand that. And I'm going, well, why don't we understand it? Well, and all you got was answers that basically said, we don't know, and nobody has ever bothered to find out. And this has gone on since 1927. And so one of the things that happened is in ISO 17497, you have to measure the absorption of a circular sample in order to be able to calculate the scattering of it. Well, we had a gentleman named Ken Roy come in. He was the head acoustician for Armstrong, and he's part of ISO. And he came in and he measured his stuff, and we came up with an answer that exceeded 1. And he said, well, what happens if we do this with a square with the same square area? So we made a square of the same square area and measured it. And the answer was that the absorption coefficient went up about 12%. Same square area, okay? And then we said, well, what happens if we change that to a rectangular that is like a 4:3 ratio? We did that, and it went up about another 10%. And then we decided to make it like a 8:2. Okay, so a different function, and the more we changed the configuration of the absorption, the more the absorption went up, and then it started becoming a large amount. Okay, this wasn't a small amount like 1 or 2%. This was like 20 and 30%. Okay, and finally, I told the guys, I said, well, let's just take these and break it up into 2 foot by 2 foot pieces and just scatter them around the floor. It's the same square area, so it should say measure the same as everything else does. And what we found was the absorption coefficient was almost double. And that was in 2009 when I gave my first papers on this. And
that was that edge effect that you were looking at, yeah?
Right. And that's what we found. The edge effect was much larger than people thought. In fact, what we found when we did the actual measurements and the work on it was the edges actually made more absorption than the actual material did, which was kind of like, okay, so then, when you ask that question, the next question comes from you is, what happens if we just measure the edges? So we made samples made out of ultra dense wood that was covered with marine varnish. So basically there's no absorption of these things at all. Nothing. But what we found was just because the edges were there, we got an average coefficient of about 0.1 out of just edges. There was no material of any kind, just edges. So it started us thinking that perhaps we can predict this, because what we did is we took all these different experiments we did and we plotted them on an R-squared regression for linear regression. And what we found was we ended up with R-squared regression numbers of 0.999 from 125 hertz all the way to 10K. And I presented these papers at the ASA meeting in Miami in 2009. And I was the session chair, so I had the advantage to say, you know what, I have 2 papers, I'm going to do them one after another, and I'm going to do it at the very end of the session. So I did that. And I was getting ready to leave, and this gentleman was walking down the aisle towards where I was standing on the stage, and he was wearing a lime green jacket and a yellow pair of pants. And he had a cane, and he walked up and he says, Mr. Sauro. And I said, yes, sir. He says, I'd like to introduce myself. My name is Leo Brandt.
Oh, wow.
Yeah. So the funny part was, I I thought Leo Brandt was dead, okay, because he was writing papers in the 1930s, 1940s,
Yes.
and Leo, I came to realize, has a great sense of humor.
Yes.
Because he looked up at me, and my jaw must have dropped all the way down to the middle of my chest somewhere, and he says, "And I'm not dead." And I said, "Well, I'm glad to meet you." He said, but he says, "I have a bone to pick with you." And I said, "Oh God, okay." My first paper, and I'm going to lose it to Leo Brandt, okay? And he says, "I have a bone to pick with you." He says, "I was going to argue with you about every one of your conclusions until I saw your R-squared regression."
Oh.
And he says, with a 0.999 R-squared regression, he says, I can only think of two things. One is you drew the lines first, and then you put the dots on them. he says, or you actually figured out what that effect really was. And he says, I'm going to give you the benefit of the doubt, because he says your formula was in basic algebra, the first 3 months of algebra you learn. Yes. And he says, my experience has been, the more complicated the formula is, the more bullshit it is.
Yes.
So he says, it's the simple things that actually count. And he says, yours was simple enough where you can do arithmetic, not even algebra. So he said, I think you've done it. So I was just flabbergasted this guy would come up and even talk to me. But I also was teaching acoustics at the University of California, Irvine, and I was using a book that a lot of people use in the United States for college by a guy named R. David Egan, or Architectural Acoustics, and a black and white picture of it, type of thing. And again, I thought David Egan was probably some guy around 70 years old and probably close to being dead, because I'd been using his book for 10 years. And there's this guy behind him with his wife, and he looked like he was probably in his late 40s. And he walked up and he said, "My name's David Egan." And I was like, these are the two guys I looked up to the most, and he was telling me, he says he felt that he was ready to argue also until he saw what Leo said. And he says, I agree. He says, it's pretty hard to argue with certainty. So he says, I think in this case, he says, you need to follow on what you're doing and continue on, which is what we've been doing for the last 13 years now, is we've been doing follow-ons to this. And I was actually supposed to go to the events coming up in Torino here in September. I think it is not in August in Tokyo, and I had to back out. The papers they were supposed to be due here a couple of days ago, but I had to back out because financial reasons. I can't make those trips; it's too expensive. So at this point in time, I'm going to be doing these papers anyway and posting on my website like I have the other ones. But what we've done now is, between myself and another gentleman, is we figured out a way of doing this set of tests that we're doing, where it took two tests. It took the monolithic test that we always done, and then breaking it up, and then we figured out what the slope was between the two tests. Okay, we've now figured out a mathematical way of doing that. So now we have a formula that matches up almost exactly with the results we're getting, and we can predict now what any size piece of absorption is and what the configuration is. So it can be a square, it can be little patches here and there, and we can tell you exactly the amount of Sabins there is in absorption. But you can't use just the absorption coefficient, because that is not a true number.
Ron, I'm sorry to interrupt. If you can just maybe give us a perspective as to what is the kind of order of the equation, just to understand.
Yeah, it's what it is to put it in edges. Basically, the material has what is known as an apparent area. So if you have an area that's 10 foot by 10 foot, the edges, because of the length of the edges, the longer the edges are compared to the area, the more they have an effect. So once you calculate what the length of the edge is, then you calculate what the apparent area would be if you make a triangle. And it makes it, as you go farther and farther out by the wavelength, it becomes less and less effective. So the wavelength determines how much additional apparent area there is, and then it calculates and gives you the absorption constant at that point in time. And we prefer to call it absorption constant because it does exceed 1. in many cases.
Right.
And in some cases, it exceeds 2. Okay,
Wow.
because of the apparent absorption. So if you look at 25 hertz, you're talking about a wavelength that is roughly, again, I'm sorry for using US numbers here, because I know we're kind of the other guys out there, but 45 feet long, which is a big wavelength. Okay. So what this basically says is that anything else out there is within 45 feet, then it is affected by this piece. So if you have another piece that's out there 10 feet out there, that is also affected by this piece as well. And that increases that absorption as well. That's why we see these increases in absorption that are so big. So I think at this point in time, we've got a pretty good handle on this now, and we'll probably be showing this particular equation probably in the next 3 to 4 months in a release to the ASA, AES, and Acoustic all at the same time.
So
And
you did mention, Ron, that even with there being no acoustic material, just breaking it up into smaller edges got you a bit of absorption. So is this going to have a really big impact on architectural acoustics, especially in spaces which are, quite challenging? You just, everybody wants marble and glass and all. So what if you broke up that glass into smaller pieces with a lot of edges? You'd automatically get absorption.
Yep.
Yes, that's one of the big, we were talking about earlier, what we think things happen and what actually happens is 2 different things.
Right.
That's one of the things that John and I have been talking about now for a couple of years, is all these things that we didn't know did certain things. We actually have found out that what we thought they did, they don't do. And what they do is something we never thought about. So yeah, you can actually treat rooms with lots of edges and get an apparent absorption that is equal to about 0.1 or 0.2. It's not a lot, but it helps. Every little bit helps in this situation, especially if you have a lot of them.
In fact, Ron, Mazi, one second. Ron, actually, you preempted my question, which I wanted to ask you. In fact, this is something that has been in my mind for quite some time in terms of seeing NRC figures of greater than 1. So I just heard you saying that there's a possibility of getting these noise reduction coefficient values, which are much greater than 1. So while theoretically it might sound a very vague statement, but I'm able to understand on what basis. So would you want to rephrase it as not calling it noise reduction coefficient? Because coefficients typically you would tend to want to have it between 0 and 1. So I like the term that you use. You call it constant.
Well, I'm not the first to do this. Just to give you a heads up, the guy Wallace Sabine is the guy who invented our business. He did not invent the absorption coefficient.
Right.
Okay. Everybody says Sabin did it. The problem is what people don't realize is there were 2 Sabins. Wallace was the guy who discovered absorption. His son, Paul, or not his son, his nephew, Paul Sabin, is the one that came up with the idea of the coefficient. And he's the one that opened the laboratory called Riverbank. And this was not done by Wallace. This was done by Paul. And when Paul presented the idea of a coefficient in 1927, he was called out on it at the same meeting. So I've discovered something in reading all these papers over the years, is that we are much more gentlemanly now than they were back then. Because a gentleman named Chrisley, who is also very well known, said basically in the paper right after Paul's paper, when he put out the idea of an absorption coefficient, he basically said in his paper written, that Paul Sabin is an idiot. I mean, it was like, I'm not sure that anybody ever said that I've ever heard, but he actually wrote in there that he was an idiot, because he said this could not be a coefficient. This has to be a constant of some kind that could be used mathematically. But as soon as you say it's a coefficient, you restrict it. So what happens is if you have absorption that is in excess of 1, you have to restrict it to 0.99. Therefore, when you reverse the thing, the amount of Sabins is never the same amount as what you measured. And that's where the problem lies, is, you only have a 3-part equation. And that is the absorption coefficient is determined by the amount of absorption divided by the area. Okay. If the number is in excess of 1, then the divider cannot be correct. And that's where the problem lies. We've always said that's the surface area. And what it is actually a ratio of the length of the edges over the area. And that's what the problem is we never had mathematicals correctly. And if you go back through all the papers, there have been a little over 128 papers written since 1927. And they all do the same thing. They all observe this thing. They all see this thing happening, but they never bother to figure out how you can use it, or how you can calculate it. What they try to do then is go and try to marry the reverberation room measurement with the impedance tube measurement. Okay, and one is a direct measurement with the energy coming direct on, and the other is a random. And they are not compatible, and they will never be able to be measured or to be married together. They are completely different things. And that's the one thing people don't understand. They keep trying to do this. So we were the first people to go and actually figure out exactly what it did and how can we use it. And that's why we feel pretty good at what we did. But it was really surprising to find out that people didn't know what it was. They really didn't want to know what it was, because I'm also on the ASTM and ISO committees. And what we discovered is, in spite of the fact of what the facts are here, nobody wants to change the standards, because in the standards committees, there's 3 groups of people, always. There's manufacturers, there's laboratory people, and there's users. Users want the latest information. They don't care how you get it. Manufacturers don't want to spend the money to redo all this stuff after 100 years, because you're gonna have to measure everything, is what they're saying. So that makes it impossible. And then you have laboratory people who don't care. Just tell us how to do it, okay? And we'll be happy to do it. We're going to give you answers based upon your things. They don't care how it's done, because they're not that part of it. They're not involved in that end of it. So what's happened is,
I think you're opening a can of worms in case you attempt to do anything further.
Take my word for it. You never want to be in the position I was in, because people hate you forever. Okay, because they're not happy. And I guess I'm 77 years old, and to be honest with you, I'm at the point where I don't care whether you like me or not. Okay, these are the facts. Deal with them. Okay, because they're not going to go away. And all that's happening here is this new formula takes away the idea of doing a second measurement. So now we can use the original measurements, and we can add in the perimeter information and change that and predict what's going to happen, which is going to greatly make this more acceptable. So now we're starting to see this being accepted more and more by ASTM and ISO as well. And I would predict that you're probably going to see these formulas probably get used a lot more by consultants over the next 5 to 10 years. But it's like anything else in our industry. It takes about 2 generations before they're fully used again. So I would imagine all the stuff we're doing right now, you'll probably see first people using it probably this year, the next few years, but you won't see the fully used for probably 2 generations beyond us, because we're a business, or we're a science that changes very slowly. Right. In spite of the facts.
So, Ron, would you like to touch a little bit upon your large room acoustics, or like stadiums and arena acoustics? Because John's going to talk about small room acoustics in a little while post that. So we could put things in a little bit of perspective as to your area of expertise, and also the evolution of ease and how you came about to be part of that team.
Okay, let's talk about large room acoustics. In large room acoustics, you're making assumptions that the fields inside the room are going to become diffuse. Okay, at some point. Okay, that means you can now predict what these reverberation times are by using the Sapin formulas, or the Airing formulas, or the Fitzroy formulas and stuff like this. But those all make assumptions. And one of the things about acoustics is assumptions. Okay, I think you all know the old word about when you assume something about something. Okay, you end up putting yourself. Yeah, Carter knows what I'm saying.
You make an ass out of you and me.
You got it. Take my word for it, the field of acoustics has done that more often than you can imagine. So basically what happens is you have to make some assumptions, and one of these is that we're going to become diffuse at some point. If you look at the Sabin equations, you cannot have a reverberation time that is less than 1 second. That just doesn't exist. It doesn't meet the criteria of a diffuse field. So therefore, we measure things in our rooms between 1 and whatever time you have. But we also look at it from intelligibility points of view. In most cases, if you want high intelligibility, you're going to have somewhere between 1 and 2 seconds. The problem is people look at these numbers and they assume they mean everything. But the problem is they are proportional to the size of the room. So a 1 second reverb time in a room like a classroom is going to be excessive, where a 1 second reverb time in a cathedral will be too short. Okay, so the assumption has always been by people who work on churches or big facilities that you have to have at least a 2 second reverb time because that's what makes an organ sound really good. Well, that's nice, but what makes an organ sound really good is the opposite of what makes the voice intelligible.
Right.
So as a architectural acoustician, I have to make everybody equally unhappy. And that's how I look at it. It's like we're all trying to please everybody. No, in our business, our job is to make everybody equally unhappy. That way, the organist doesn't get his 2 seconds and screw everything else up for everybody else. The choir doesn't get theirs exactly the way they want to. And when everybody's equally unhappy, then you probably have a reasonably accepting church that sounds reasonably decent. Okay, same way with a concert hall. If you have a concert hall, you need to know what kind of music they're playing. There is a measurement called the C80 plot. Okay, this is the direct sound plus 80 milliseconds of reverberant energy. Okay, if you use this number, 0 is basically saying there is no difference between the direct field and the reverberant field. This is perfect for a large pipe organ because you want the pipe organ to sound like it comes from everywhere around you. Okay, therefore the reverberant field is as necessary as the organ itself is. So I always tell people, look, C80 is the intelligibility of music. That's the best way of putting it. So if you're familiar with terms in music, you have what we call a run, where you have a lot of fingers going down the keyboard, going all the way down, right? Okay. At 0, you have the run, but it sounds like a glissando. So you can't detect individual notes. All you can detect is a tone that rapidly changes timbre, going from high to low or low to high. Okay, so it sounds like a slide, like taking your finger and just sliding down the keyboard. Okay, so between 0 and 2, which means 2 dB difference of the reverberation being less and the direct field being higher, that's great for organ. Now between 2 and 4, that's great for something called a plucked string. So if you have a violin and you pluck the strings, or a guitar, that has the right amount of attack and decay to make the sound good. Okay, so that's good for what we call basically a plucked string, I'm sorry, I was wrong. It's early morning for me yet. This is for a stringed instrument, like a symphony orchestra. Okay, the next one is a bowed instrument. There you go. So you have a slow attack and a reasonably quick decay. Okay.
Would you classify a viola in that category? Viola or cello?
Yes. Those are bowed instruments.
Right.
Okay. So that's good for symphonic music. Okay. So you have organ music, you have symphonic music. The next thing you have between a 4 and a 6, okay, is what we call plucked instruments. So guitars, this type of thing. Okay. And that has a quicker attack and a quicker decay. And then the final one is the direct sound is 6 dB better than the reverberant sound is. And these are for percussive instruments. So drums, believe it or not, things like piano, any kind of instrument where whatever it is struck. So you have a piano string with a hammer, okay, this type of thing. So yeah, xylophone, anything is struck with something to make a sound. And this allows music for what we call rock and roll. Okay, that means very fast attack and very fast decay. So you can hear the individual notes of a run. Okay, and the more distinct those notes are, that the more the direct sound has control over and above the reverberant control. So these are all things we have to learn when we do large room acoustics. We have to learn about envelopment. We got to learn how sound comes from the side walls and envelops you within a certain period of time. So if it's less than 40 milliseconds, then it helps you increase the intelligibility. If it exceeds 40 milliseconds, then you have an echo, which decreases intelligibility. So these are all things that don't occur in recording studios because they're just too small. Okay, that's the difference between what we do in large room acoustics and stadiums. Now stadiums are even worse because they become free fields. Right. So it's like being outside, except that you have echoes. So you don't have a reverberant field inside of a stadium, like a closed-in stadium, like a dome stadium. There's no reverberant field there because it decays too far and it's gone. Okay, below 60 dB. But what you do have is distinct echoes coming from different places. And they can do the same job. So the more you have echoes, the more you have deterioration of intelligibility. So this is the difference between what John and I do. I work on larger facilities like that seat, I'll give you a hint. Since you're in Mumbai, the largest job I ever worked on was New Delhi.
Okay.
And you guys were celebrating your 50th independence, I think it was. Okay. Okay. Remember there was a big
1997, maybe 1997.
Right. Yeah. It was the late 90s. Okay. You remember, right? There was a large parade going down through downtown New Delhi. And you saw, I think there was like 3 or 4 million, 5 million people there for it.
Wow.
If you looked around there, you saw speakers on poles everywhere. That was the design I did for the Indian government.
Nice.
So that's the largest event I've ever done with 7 million people, I think it was. Okay. And the funny part is it got put up like 2 or 3 weeks before the event, and it was torn down immediately after the event. Okay. So it was a temporary job. So that's the kind of jobs I do is stadiums and arenas, things like the Olympics and stuff like that. I leave recording studios and listening rooms and stuff to people like John, who has a very good control of how that works and things. Okay, so I think in this situation, all I can do is inform him of materials that he can use in his field. And this is, John, I'm if you don't mind, I'm going to at least release one thing that we talked about. Measuring. Okay. Many of you use what we call 706. This is Owens Corning 706 fiberglass, 6-pound density. John was hoping to keep this for his book, and it's fine.
Yeah. Please go ahead.
Yeah, this is too good. Okay, we've been for years talking about low frequencies need low density. So we're talking about, pink stuff, very fluffy and stuff like that. And it doesn't work very well at low frequencies. It reflects low frequencies. I thought the same thing. I taught the same thing for years. John taught the same thing. We built things based upon all that. But John has put his own self on the line here. He's spending well over $30,000 in measuring materials that are just normally used, that nobody else ever measures. And we've been doing them at our place. So we're measuring them not at 100 hertz or 125 hertz, but at 25 hertz. Wow. So we're able to tell what's going on in the low frequencies. And I just got finished doing these for him about a month ago, I think it was it?
Yeah, yeah.
And what we found was this: there is a specific thickness, and if you do any design work in your own studios for your own places and stuff like this, keep this in mind: 4 inches of 6-pound density Owens Corning or whatever brand you have, NOF or whatever it is, will give you a flat response of absorption of about 0.8 coefficient, okay, from 10,000 hertz all the way down to 80 hertz.
Wow.
That's now you know one of the things that just has occurred, and this is, even for me, it was like, I'm not sure I believe that, so I tested it 5 different times in 5 different ways, and the answers were the same.
Wow.
Yep.
So all I'm telling you right now is we learned something again that was supposedly wasn't going to do that, and all of a sudden it's like, oh, okay, this goes all the way down to 80 hertz with just plain old 4 inches of it. And it's like, this is just unheard of. Nobody ever thought it would go this low under any conditions, because the latest data we always had was 125 hertz or 100 hertz. And the assumption was it was too dense to do 80 hertz. No, it actually works very, very well at 80 hertz for an overall absorber. It's not the best at 80 hertz. 703 is still better, and some of the fluffy stuff is even better at those frequencies. But the facts are, you can have one material that will do the majority of what you want it to do. And that is a very big change in how we design things.
Yeah.
So these are things that, I've been trying to share with John for the last year or so, because these are things that we also use in our large rooms, large churches and stuff, for controlling acoustics. And these are applicable to studio design as well.
Indeed.
So, yeah, I think he and I were talking about this with the curved rear wall and stuff like that. There's a reason for it. And I got a kick out of it. John and I were talking about this a couple days ago. And that was, somebody asked him, what's the formula for calculating the curve? And I looked at him and I said, John, I said, whoever's asking that question doesn't understand what we're doing here. Because all we're trying to do is change a planar wave to a curved wave. That's all we're trying to do. There is no formula. It doesn't matter. You just curve it from the corner to corner and kick it out about 1 foot. That's all. There's no magic. There's no formulas. There's no, what's the frequency range? It doesn't matter. All you're trying to do is change that reflection so it doesn't come back and hit you in the back of your head. Okay. And what people don't realize in our industry is sometimes just because you do one thing doesn't mean you can extend it forever. Okay. There's always limits to what it can do. And you can't just take something and run with it and go, well, if it does it here, it must do this over here. The facts are that it doesn't work that way.
we tend to extrapolate a lot of information which is incorrect.
Yes, and that's one of the things that I'm trying to get away from in this situation is to realize that when we extrapolate, we sometimes are extrapolating way beyond what the physics will allow. And that's why we test, to tell you what the limits are as well. I see there's a question somebody asked about with densities. In this case, this was 6-pound density, very dense. Okay, that did this. Now, like I say, lighter densities will do a better job at low end, but as far as an overall absorption that's even, this is the best I found so far in many years of measuring stuff. 2-inch doesn't do as quite a good job. It drops off at a higher frequency. 6-inch doesn't make that much of a difference. Okay, so what happens is you have less and less effect as you get thicker, and the cost of adding that extra 2 inches is more expensive than what the gain is you get from the effect.
Exactly. Yeah.
Okay, and this is the one thing we have to learn is just because 2 inches does good, 4 inches does good, 6 inches is not going to do much better. Okay, so that's the one thing we've learned is excessive thickness is a whole waste of money and time of buying stuff and taking up space, and the effect you get is only about 2 or 3 or 4% better.
But if we wanted to improve that using the same thickness, what about layering different densities? Would that help?
You have to test it. We have some testing planned.
Okay. Yeah, we actually tested. We actually did a test with 2-inch 703 and 2-inch 706. Okay, and I can tell you that some of the answers there will be surprising. John is going to be putting a lot of this in his book. And John, I have to tell you, I got a commentary yesterday. Instead of waiting to do your book in one big 12 swoop, everybody's telling me the same thing. Let's publish the ideas behind your book first, publish a second book with the coefficients and stuff of a whole bunch of materials, and then do a second or a third volume with the more materials as we measure things, because it's like
that might be the best way to go. It's taken us forever to get this out.
Yeah.
So
So that was a suggestion made by somebody in the industry who said, look, let's get this stuff out there, because what you're saying is you're discovering a lot of stuff that we should all know about, because it's going to change the face of our industry.
Absolutely.
Yeah.
So let's get it out there, So
Okay.
I was gonna talk to you about that, but this has happened in between. So as the case may be. So
let's talk about it this as soon as possible next week. I want to get rocking on it.
So
anyway.
so what's happening, Kartik, is you're seeing the effect of all this stuff in real time.
Right.
This is what John and I do when we talk all the time.
We are privileged to have cutting edge technology being discussed as we do this session. So that's a real privilege for us.
Yeah, you're right at the bleeding edge here. Okay, right now. And this is stuff we're discovering in the last months or so. So, you're hearing results that other people have not heard yet.
Yeah.
So, Ron, just if you could briefly, just before we move on to John, could you briefly touch upon your association with ease and how that whole thing came about and your contribution to ease? I mean, just in a nutshell, kind of.
Well, it's kind of short, but what happened was ease goes back to 1989, 88 and 89, when the first version was. Wolfgang was in East Germany at the time, and he was designing things for the communist government there. And he developed this software package that basically did basic acoustics. Mostly it had to do with how to put speakers in places and make them work. So it was EASE is a acronym for electroacoustic simulation for engineers. Yep. Okay. I was looking as a contractor for something to help me design, and I looked at things like Bose software. At that time, Bose had software, JBL had software, Altec Lansing had software, but the problem is all these softwares were based upon using their speakers, and that was it. So if you bought the software for Bose, you had to use Bose speakers. JBL, you had to use JBL speakers. EASE was the only thing out there that had a generalized database. So, but it was also the most expensive of the four softwares out there. So it took me a while to put up, $700 for that time to buy the EASE Junior, because that was a lot of money. Wow. So I bought it, and I built my first model. And the way the model was back in those days, all the data had to go in by way of tables. So if you built a face, you had to put vertices in first, and they had to be described in a table in X, Y, Z coordinates. So you have three dimensionals, and you build this thing in space in your mind, because there's no pictures. EASE didn't have pictures at that time or of the building. So all you had was this. You had to measure it, put it in a piece of paper, and say, okay, hook this together, and we have a face. And you had a restriction of 4 vertices per face. That was it. So if you couldn't make it, so you made it with a whole bunch of little squares and stuff. And if you made it with 30 or 40 faces, you were doing a complicated model. And to be honest with you, being a stupid guy, I always like to push things. Okay, I decided to try to build a model with 200 faces. It took me a little over 2 weeks to do it. Okay. And I did my first model that way. And one of the things that happened was I wanted to put some windows in, and it said in the model, you put them on the thing and you draw them, and then you sit there and just, it would automatically calculate the RT60. Well, I grew up at NASA, which means I trust computers as far as I can throw them. Okay. Which is not very far because it's all garbage in and garbage out. And so one of the things that happened was I had programs where I could calculate it by hand. So I calculated the RT60 of this room with everything in it, and then I did it with EASE, and the answers were completely wrong. So I contacted Rinkus Hines, who was selling the program, and I said, this is a wrong program. It's not calculated correctly. And the guy who was running it was one of his students. And he said, it can't be. And I said, well, it is. And here's the answer. And I sent you all the stuff. And he says, I have to send this off to Wolfgang. And I'm kind of going, because he was in Germany. And, at that time, we didn't have internet and stuff like that. Okay. So he sent a letter to Wolfgang and said, this young guy says your program is wrong. And all I know is at 3 o'clock in the morning, I got a phone call.
Wow.
And I answered the phone, and he says, is this Mr. Sauro? And I said, yeah. He says, this is Wolfgang Honert. And I was kind of going, who? And he says, this is Wolfgang Honert. And I'm kind of going, okay. You do know this is 3 o'clock in the morning. And he says, I never thought about that. He said, where are you at? I told him. So as the case may be, he said, I was told that this guy said that you said I was wrong. And I didn't know who Wolfgang Honert was. I had no idea. Okay. I was a guy who put sound systems up. That was it. Yeah, I sold things. And I said, yeah, you're wrong. And he said, you do know who I am? I says, no, I don't care. You're still wrong. Okay. And everything went silent for about 35, 40 seconds. And he said, at the end of 35, he says, you're right. I was wrong. And I'm kind of going, okay. I said, so what are we going to do about it? He says, well, at that time, E's came on a 3.5-inch disc. That was it. And it had only memory 1600 or 640 kilobytes. And he says, I will send you a new version of E's with this correction. Because he said what was happening is it was taking the absorption coefficient of the window and laying it on top of the material and not subtracting the material in the same area. So he said, we'll figure that out. So he sent me that. So when we were talking, he said, have you ever thought about beta testing software? And I'm kind of going, no, not really, but he said, would you mind beta testing E's? And I said, sure. I said, he said, I'll send you a full version of E's if you'll do that instead of E's Junior. And I said, yeah, I'll take it. No problem at all. Just send it to me. So I ended up being the first beta tester for E's for the first 3 years.
Wow.
And Wolfgang and I became really good friends over a period of time. And I was involved in the development of E's through E's 3 and E's 4 and all the rest of the stuff. In fact, if you have E's 4 and you have the manual, I wrote the incomplete manual and the help files. Okay, nice. So there's like 300 pages, give or take a little bit, because it was like I was teaching classes, and I found out that you have to teach people basic acoustics for them to understand how to use these programs. And what I found was that they were wrong, and it was all based upon wrong databases. And that's why I do this now. So I know one of your questions was, how accurate are these things? They're only as accurate as the databases are.
Yes.
And the material database is inaccurate at best.
Yes.
Okay. So, so you're going to have to learn how to compensate. That's what scattering effect was. Scattering was an additional absorption that was added into the program to make up for the lack of absorption data correctly. Okay. And what we found is this edge effect is the scattering. So this is the diffractive effects of the edge that's added on. And what people don't understand is absorption today is either frictional, which is what fiberglass is, and sound goes through it and slows down and gives up heat. Okay. You have diaphragmatic, means you cause the surface to move, and that causes friction on the edges where it's bending over and over, and it gives up heat. Therefore, it's absorptive. Then there is resonance, where you have a pipe and air goes back and forth, and he compresses and decompresses, and that causes heat inside the air from the compression, like a shock absorber. That's absorption. Diffraction is also the same thing. Okay, and that is when you change the direction of sound in another direction, you change the phase when you do that. And when you change the phase, there is a paper written in 1960 at Ohio State University on radar. And it showed that if you took a radar wave and hit an edge and bent it, the edge would melt and get red hot. And somebody said, well, it's the material because it's steel. So they changed it to wood. It burned the edge. They changed it to fiberglass. It melted the edge. And what we discovered was it was not heating up the material. It was heating up the air right around the edge, which means when you bend it and change the phase, you now have losses based upon phase. And when you have losses and give up heat, what do you have? You have absorption. Is that right? So now we have a fourth method of absorption, and that is diffraction. And that's exactly what scattering was, okay, was a diffraction. So if you measure the absorption correctly, okay, I'm losing somebody here.
Anil Gupta, could you please just mute your mic, please? Anil, please mute your mic. Thank you.
Yeah. So basically what happens is if you measure the absorption correctly, you will not need this scattering effect. And that's what we're trying to tell people now is if you do this correctly and take into account the length of the edges and the amount it adds to it, that you will not need that scattering stuff. So now you can use absorption like you're supposed to be. Okay. If that happens, then the formulas in these programs, and this is EASE, what do you call it, Cat Acoustic and Odeon, they all have the capability of being extremely accurate, provided the database behind them is accurate. The problem is they're all inaccurate at this point in time. So this is what we're fighting for right now. We've been told by people at EASE that as soon as we have a standard that we can apply, a call out a number for it, that they will apply these new formulas, their programs, but we need to have it accepted as a standard number. So we're working at ISO to have that done, and we're working at ASTM to develop a diffraction standard, diffusion standard for surface reflection is what it's called. And so we're measuring diffusion now like we do speakers. Same balloons and stuff you see in EASE. We can do the same thing in diffusion. So you can take a wall of diffusers, measure them and put them in, and calculate them as a cluster, like you would a speaker cluster, and come up with a single balloon of the entire array, and use that in these programs. And that's never been done. It still can't be done officially, but it means that there's a workaround that allows you to do it. So if you guys are ever interested in how we can do it, I'm sure we can have a discussion about that, of the easy way of doing that. But there is a way of making it work in EASE and other programs using the GLL functions and making diffusers that do that. And we have about 200 diffusers that we've measured in the last year. So so they're available out there, and this is what we can do. So I think I've chewed up so much time. I'm sorry, John. it's your turn here.
It's okay. No, it's great.
Thank you so much, Ron. That was really enlightening. And John, over to you now. It's your turn to enlighten us on small room acoustics and basically of the process you go through when you're designing. I know you design studios and space, but we're going to speak about a home theater room, and how do you go about with ratios, room ratios, kind of absorption, diffraction, and all the kinds of things that go into designing a home theater room.
Okay. Well, when you're designing, let's take the home theater for example. The first thing we need to know is, if I'm your consultant, let's say, first thing I need to know is, what is the purpose of this home theater? Are you wanting to experience the film like you're there, like you're really, like the producer wanted to do, or do you just want to be able to watch a movie and have popcorn and chat with your friends and whatever? That's a different situation. What I specialize in are rooms, immersive rooms. You go in, well, you're there. You're like, if you're watching Star Wars, you're out in some distant galaxy. If you're in a war film, you're on the battlefield. If you're in a spy film, or whatever, you experience that. You experience everything that they had written into or programmed for the film. Let's see. So, just trying to, here I am. Let's go. So, room ratios. You really need to have a good room ratio because that they can come back to bite you. A lot of times if you, especially in the low frequencies, which are extremely hard to control using acoustic absorption, diffraction, diffusion, etc. If you have a problematic resonance, it's a ringing or a tone, basically. You want to avoid that at all costs. So you want to get your room ratios where you have a good distribution, a smooth distribution of the sound, so that everything's even. I've often said that a lot of people want to get rid of the modes or kill the modes or whatever. No, modes are your friend. They support the music. They support the sound. So they bring it. Otherwise, you might as well go out in your backyard and listen to your speakers outside with the forest behind you or whatever, the fields. That's how it sounds when you don't have room modes. It's not as enjoyable, really. You get more immersion if you're in an enclosure that supports the sound, you know, and so you have a certain decay in the room. You don't want any reverberation or a long decay. You want to, most home theaters, most recording studios, mixing rooms, etc. These are small room acoustics. They're pretty tight, or at least mine are. They don't have any room sound of their own. There's enough, I'd say you should have enough room sound or reflections or diffraction so that your primitive brain senses that you are in a room or that you have boundaries there. You don't want to go into your home theater and feel like you're in an anechoic chamber. You want to feel like you're in a room, you know, basically you're comfortable. It sounds okay. So
what would you say would be the typical, like, let's say RT60, which is not actually for small rooms, which you had this thing, but
as Ron said about concert halls, so it depends on the size. So I have a room mode calculator on my resources page on my website. Anybody can download it. You plug in your numbers, your length, width, and height, and do the macro calculations. You have to Control Shift S and Control Shift C, and then it'll calculate for you. You have to use Microsoft. Sorry, you can't use another program to run the Excel because of the macros. But if you do that, it'll tell you what RT60 you should hit when it's treated properly. It tells you down there. I've actually got too much information in that spreadsheet. It confuses a lot of people, and I apologize for that. But I put my musings in there. I go, oh, let me see. I wonder if I should put this information in. It eventually gets sorted, and never mind. But the RT60 you're looking for is listed in the RT60 box down there. You have to scroll down under the regions. It talks about regions. You can see the distribution. You see how it meets Oscar Bonello's criteria, which is held true. Actually, Bonello wrote the criteria, I believe, in 1980 or 1979, and I still use it. It holds. It's a good one. So if you can meet those specs, you got a good room. If you need to change something, do so, but try to change it so that you don't make it tiny. I've done some rooms that we reduce one wall by an inch or 5 centimeters or whatever. That's fine. But reducing it a lot or changing it too much, then you run into volume issues, and you don't want a home theater or a mixing room that's less than 1,500 cubic feet or 42 cubic meters. That's the minimum. And then you can experience a pretty good sound in there. When you do have a small theater or a small room, you're limited by that volume enclosure as far as what the lowest frequency can be reproduced in there. It's dimensional dependent. Okay, you know how long a 20 hertz wave is. It's pretty damn long, so that you're required to have a room at least half a wavelength of 20 hertz if you want to get down to 20 hertz of just wave energy. Now,
John, can I stop in 1 second on that?
Yes, please.
Just so you're aware, you can put a speaker in the room that will give you 25 hertz, and the speaker will make 25 hertz, but the room itself will not support it.
Correct. Right.
So you're not going to see any additional room emphasis coming from the room itself, because you can't support that frequency. It's not big enough. Okay, and that's where the problem lies. Is people say, well, we want our room to be able to do this. Well, you don't need the room to do it. You need the speaker to be able to do that, but just be aware that you're not going to get any additional help from the room. And that's where it comes down to.
It's going to be as though you're outside listening to that,
yes,
that frequency. Because excellent.
So is this what they talk about when they say room gain? So there wouldn't be any room gain at that frequency?
Correct. No room gain there. Yes, that is correct. It's where your modes support the sound, and you get a little help there. Room gain. Too many folks have too much room gain because they don't have enough treatment. But
yes.
Now, when you have a very small room and you want to hear 15, 20 hertz, you're not going to hear 15 hertz, but you're going to feel 15 and 20. So I don't think I can hear 20, but you feel it. It's there, you know. Oh yeah. But what you need in a small room is a pressure transducer similar to your earbuds. Earbuds are pressure transducers, and you put them in your ear. And how do you hear bass in a tiny ear canal? How does it, you're not listening to waves, you're just listening to pressure changes. And the earbuds are very good at doing that. As soon as you pop them out, you break the seal, the bass is gone. See, same way with say you take a sealed subwoofer, for example, it can do pressure changes that you can feel in a small room. You can feel that pressure change. So that's just thought I'd mention that, because if you got a home theater and you went to all these big subs and you get these big ported subs, they don't tend to be that effective. Am I right, Ron? In a small enclosure like that, they tend to the sub enclosure, if it's a ported sub, tends to disappear, and then you got a speaker hanging in the air, and the pressure behind and pressure in the front just cancel each other out at that.
The speaker will give you the frequency, but the room will just ignore it, basically. So you'll hear the speaker, but you're hearing a pressure change in your eardrum. Please keep in mind how big your eardrum is. Okay, your eardrum is less than 1/4 to a 1/2 inch in diameter. Okay, what is the frequency range in which it actually works? It's somewhere around 6 to 8K. So all these other things you hear that are lower frequencies are all the harmonics of these frequencies that you can hear, because your ear just can't respond to that pressure change that way. That's why you have the ear canal and stuff like that, to be able to monitor that, keep and control that.
So as a corollary to what you're saying, John, are you saying that for a home theater in a small room, sealed subs are better than ported subs?
Oh yes. Oh yeah, way better. Way better. Because you're going to get the pressure.
There is a question which is there from Sandeep. Sandeep, if you can unmute yourself and just ask the question. It's a very relevant question, or rather a relevant point to this current discussion. John, if you permit, I'll ask Sandeep to ask the question.
Go ahead.
Sandeep, please go ahead. Sandeep, please unmute yourself and ask the question. Or
Yeah. Can you hear me? Can you hear
Yes.
me, Karthik? Yeah.
Yes,
okay.
we
Yeah,
can.
you
Yes, we
Yes,
can. Go
we
ahead.
hear you.
go ahead.
Yeah. So the thing is that I mean, especially on the infrasonics and coming to the regarding to the room size, and what I have observed is that you know, if you take a larger subwoofer, because which we have done earlier with a couple of installations, I'm talking about a much larger subs. I'm talking about close to 24-inch subs, which can go basically down to 5 hertz in an open environment. You know, when it comes to the room of some X size, you know, the lowest cutoff frequency what is being observed is like, you know, the quarter wavelength of bare minimum to experience, you know. For example, if you say a room has got 25 feet in length, so then, you know, it can't go below the quarter wavelength, you know. It's like it can't go below less than 10 hertz because the pressure itself is not being observed to you know, to develop the pressure in the room. You know, the size of the room is not such.
Yeah.
So this is something which my observation has
But it's
happened.
it's not a brick wall at that halfway. It's not a brick wall. You get wave partials, you get all kinds of things happening that aren't necessarily quantifiable in, okay, it's exactly this, and it just, you got a brick wall cut off there. That's just, no. Yeah, I hear you. I understand what you're saying. Yeah.
Yeah, you have a situation where you have, like you said, quarter wavelengths and stuff, but each time you cut the wavelength, you reduce the efficiency of it.
Agreed. That's what. Yeah, the efficiency drops. I mean, that's the whole
Right.
point. Because
and
I see customers coming to us and saying, wow, we would like to have the 24-inch subwoofer in our 20-feet room. We say, no way, you can't even hear it because the pressure doesn't develop. You know?
Yeah, it's one of those things where the additional, you're going to have to pump that frequency at such a high level to be able to get the cancellation to go away.
Yeah. My observation. I just want to share this because, like, you know, this is something, the myth that you know, even an extremely small room, you know, we can generate and the pressure.
It depends on the size. Also, if you have a large air mover, like a 24-inch sub, ported in a small room, it's still going to move air, and that's going to extend a certain distance, and you're going to feel or hear that, you know. But
the problem is going to happen, Sandeep. Yeah, the problem here at Sandeep is what's going to happen is depends on where you are in the room as to what the modal response will be. So you could have cancellations and additions depending on where your head is or where you are in those kind of situations. So you could be standing there and move over 3 feet, and everything you're hearing will be completely different because of these cancellations occur because of these modal functions. So yeah, can you have it? Sure, you can have it. Is it going to be even across the entire room? Probably not.
This is the goal, or should be the goal, is evenness, as even as possible. And the maximum size of subs that I've ever used, even in large, well, no, it's 18. I've gone 18 in huge, very large, but it's usually average about 15, and 10-inch subs do fine as long as they're powerful enough, and you got a few of them. Remember, when you add another speaker, you think you're adding level to the room. 3 decibels. That's the most you can add with an identical sub. That's all. You're gonna have to add quite a few of them if you want to get it louder than what it is, or more audible. So
yeah, those people have to understand that 3 dB is not audible to most people.
No.
Yeah, if you're a trained listener, you can hear the difference, but the average person cannot hear a 3 dB differential. They start to hear differentials at around 4.5 dB.
But so thank you, Ron. So I have a scenario to work with. I mean, I just want to see, because these days lots of movies are coming with infrasonics. Lots and lot of movies, and there is a substantial demand for it. I mean, the last time I want to share my experience, because infrasonics is something which is not spoken of very frequently, because you generally don't get a chance usually to have such kind of experience. So my recent experience was watching a movie Top Gun, and watching a movie with infrasonics was like way different than just listening to the sub bass and the feeling the ultra deep, and it's something which is nice. I mean, I don't know how well it is being monitored at the time of mixing the movie, but I think that the future has got a lot of infrasonic products which come into the picture, I guess so.
Sandeep, I can maybe tell you a little bit, and I think John can tell you this too. The first movie that really took into account infrasonics was a movie called Earthquake. Okay. And they made special speakers that they put installed in the theaters that were made by Serwin Vega, I think it was. And they're called the Earthquake cabinets, and they're about probably around 50, 60 inches square and about 18 inches deep. And they were a folded horn. And they used to put them in the back row, underneath all the seats, so it would shake the building. And they were talking at frequency ranges of 15 hertz to 20 hertz at that time. But they also, each speaker was covered with about 3,000 watts of power. Okay, so it was, and that's all it did. It just strictly those frequencies. So here you have these movies that actually made you think that you're having an earthquake inside the theater. And it was quite exciting to be part of that, because when you're sitting there, it's like the whole room is moving, especially when it happens. And it was freaky for people, because I remember hearing women screaming and everything else. They thought they were having an earthquake during the movie. So so it is interesting how this, been doing it. But bringing it into the home is much more difficult than even a theater. If you have a full theater with 300-400 people in it and you're doing that, that's a different experience than if you're doing it in your living room.
But infrasonics, can be are more felt than heard, and those can be even brought about by tactile transducers, right? Butt kickers, or what you call them. So, I mean, that's really another thing up for moot. So, John, if you could continue with the more important topic, the home theater design.
Okay.
Fantastic.
As far as that, I'll say this on infrasonics, and I know many may disagree with me, but honestly, I think it's better and more convenient for everybody, especially if you're building a home theater and you want infrasonics. Go purchase some very well-designed, well-made bass shakers and screw them onto each chair. Ta-da! Problem solved. It's not expensive and it rocks. It does the similar effect.
John, if I can just add one point. So there's this chair called D-Box, which is developed in Canada. And I had the experience of sitting on a D-Box seat, which tries to emulate a certain kind of frequencies which translate into motions of the chair.
Right.
And I would say that it can be a very, very harrowing experience if not done correctly.
If what?
It can be a very bad experience.
Okay.
It can be a very bad experience if the encoding and decoding is not done correctly. It can be a very, very bad experience. So I would say that infrastructure is something which needs to be dealt with very carefully in terms of the implementation side, because if it is not done correctly.
But it always goes back to, it's not what you use, it's how you use it. So it's very important. It's a lot of people, I give out a lot of information. I'm always posting this, that, and the other. And some people will take it and they'll do it. They'll say, oh, that work. Okay, I'll use that. And they don't know how. And they use it and it's detrimental. And the question of the list of questions that were asked earlier when you sent me an email, Kartik. Some questions about how much diffusion, diffraction, absorption to use in the usual room. Is there a percentage or is there a formula? Not really use the Sabine formula, but at the same time, you kind of have to know what certain things do, what their effect on the room is, and what you want it to do. What I need X over here. I need this to diffract, or I need this to absorb. And so you put the appropriate thing there. And you also have to think, why do you want it to diffract over there? the result. What's the end result? So it's a little more complicated than I want to put this up over here and that over there. It's not something you want to just, oh, this looks good. You never know. You might get lucky, but usually not, you know.
Well, the point is, in the quest of trying to make the experience more immersive in nature, there are a lot of things which are done wrong fundamentally. So that's what I was wanting to hint at when I talked about the D-box experience. So it depends on the artist's intent. If the intent is correctly transferred into the end product, it could be a great experience. But if the intent is not correctly implemented, then it could be a really I had a headache when I sat on the D-box chair for one of the movies. Real headache.
I can imagine.
Yes, something to understand is some of the history behind all this. And I don't know whether, John, you know this or not, but SMPTE, S-M-P-T-E,
yes,
did some experiments in 1932 on infrasonics in a movie. Okay, and what they discovered was if you included frequency ranges of 40 hertz down to 31 hertz in the movie, it made the audience uncomfortable. So, and the way they did this, when they proved this or used it, okay, if you go back to the old movies, you will find things like Frankenstein and Dracula and stuff like that. They all have this background noise when things are going to happen. It's kind of like a low thrumming going on all the time, and it's right around 30 hertz or so. And what it does is it makes your inside your body uncomfortable. It makes you feel like there's something going to happen.
Brings up the anxiety. Yes.
Right, it's anxiety.
Yeah.
So they've been using that since the 1930s to make you feel that in horror movies. Okay, so if you're aware of it, just go to a movie, watch it, any of the old movies, makes no difference. Creature from the Black Lagoon, any of this stuff. Okay, you'll always find there's always a thrumming tone in the background just before something is going to happen, and that makes you prepared for the scare.
Yeah, that's great.
So it's just, be aware that we've known this for a long time. We do a lot of audience manipulation using sound.
Course.
And yes, I just think it's kind of interesting that we're you can talk about what you can do in home theaters. It's the same thing. If you want to watch horror movies, make sure you have a good bass speaker in your a sub bass. Okay, in reality, human really makes it difficult to hear anything a little above 30 hertz, and the way you can know that is you just listen to a 64-foot bass on an organ. Okay, most of the time you can't hear it. You can feel it, but you can't hear it. So and that's 31 hertz.
Yes.
So most of the time the human being, especially as you get older, you lose hearing acuity. So a newborn baby can hear from about 35 hertz to roughly around 20K. When you're our age, okay, I use this our age as advisedly here. John and I, the average hearing for a person our age is probably around 40 to 50 hertz, up to around 10K, and that's about it. Okay, beyond that, everything beyond that, if you claim you can hear 20K, you're not hearing 20K. You are hearing the beat frequency between 20K and something else. Okay, it's just it's because of the hardening of the cilia in your ear, and you can prove that to yourself by going out to an amusement park and trying to ride the scrambler. If you try to ride a scrambler when you're over a certain age, I never said it. My dad was always telling me I can't ride that ride anymore, and I'm going, okay, let's go ride roller coasters. I'm a roller coaster freak. Okay, what I found as I got older, I couldn't ride these rides anymore because my inner ear couldn't compensate for the change of direction as fast as I used to, because it hardens up, and it's just the way it is. You get older and you just are not able to do the same thing. That's why you have balance problems when you get older too, for the same reasons.
You probably can even have maybe a imbalance in between your ear canals, maybe.
Yes. Yeah, the cilia inside the hairs harden and they just don't move as easily. So that's why it's always a delay.
Yeah, I was talking to a client the other day about, well, I was discussing dynamic load and just and a structural loading for something, and talking about dynamic loads and earthquakes and stuff. And I said, my wife the other day, she said, I was walking down the hall. She said, "Did you feel that? It's an earthquake." And I said, "Really? I thought it was just me." I don't feel earthquakes anymore. It's a good constant earthquake when I go anywhere. No, just joking. So what shall we continue discussing? Oh yeah, the room for a theater or listening room needs to be the speakers and speaker placement are most important. Also, what you have across the room on sides is very important, because what you want, I mean, you want to hear your surround speakers, you want to hear your Atmos speakers behind and around, but you really don't want to hear anything else coming from the wall. Like this speaker over here, you don't want to have a reflective surface over here that's going to reach you, that you're going to get a phantom image off of. So that's going to skew the mix, so to speak, of the film, what you're listening to. Unless you listen to films like I do on my desktop, and I've got a 43-inch 4K screen here, and I'll listen to my desktop speakers, and then I'm close enough to where my room doesn't really mess with me. But home theater, if you're going to spend the money and build it, do it once, do it right, done. So you need enough treatment to control the sound to a point. I have a chart I made about the ideal response curve, and your room decay should also follow this ideal response curve. I don't know if not everybody's going to agree with me on this.
So I got a question.
Yes, sir.
So I generally do a lot of residential home cinemas, and I'm not that great with these softwares and readings and sound readings and analytics. How we read a room. Now, if I'm doing a home cinema and I'm selling an expensive system, say I use Scansonic speakers currently, they're handmade, they're perfect, they're amazing whenever they sound, even without the subwoofer. But when I'm doing a home cinema, what are the first initial things that I should consider the most important? When I'm marking the perfect placement for a speaker. So say it's a simple living area. They're sitting at 15 feet. I have a Scansonic speaker. That's an on-wall speaker. It's a small chassis, but an AMT tweeter with a 5.5-inch driver. Now, when I'm deciding what's the best position for these speakers, what are the basic things that I should consider for a generic living area with 3 walls and one long open end?
An open end?
Yeah, yes. So living areas in India are usually attached with a dining part.
I see.
So we have
it's difficult because you have the open end, so you don't have the support from that the length mode. Let's say the front, you've got the screen and the sides, and then it's open in behind you.
Yes.
You don't have a positional that you can set your listening position to. Normally in Dolby criteria, you're going to be sitting in the rear 2/3 of the room. That's the prime listening position. The next prime listening position is the front 1/3, which is often too close to the screen. So the rear 2/3 is ideal. You want everything based around that listening position and directed at that. Or if it's a row of seats, then you want to spread out your distribution. It gets complicated because the room affects what's coming out of the speakers. And if you don't treat the room, then you're listening to the room. You're not listening to the speakers.
Yeah, we have a saying in our industry that I don't know whether you're familiar with a company called Radio Shack. Okay, but here in the United States, it was kind of like a place you bought, a lot of junk basically. And I always told people that the room is a larger part of your sound system. So if you don't have the room right, if the room is wrong, it can make the best speakers sound like a Radio Shack speaker. And by the
Ron,
same token,
Ron, please repeat that statement. I would say 100 times. We had Norman say the same statement last time. I would wish that you make that statement 100 times, 1,000 times.
okay, yeah, I can make a very good speaker sound crappy by having a crappy room. By the same token, I can have a great room and I can have the cheapest speaker you can buy that will sound great.
Right, exactly.
Absolutely.
And so, when I hear you talk about, well, we have these speakers to do this and do that, I'm kind of going, yeah, you can have the best speaker, go out and buy, the best Genelex, I've actually had to, I think Norm has been involved with some of these things along the way too. But I tested some speakers for a number of these companies like B&K and stuff like that. And we tested them and they didn't test all that great, but they sounded good. But that's because they were always in rooms that had been treated very well. And what was interesting is I took the same speakers and put them inside of a standard living room that didn't have any treatments at all, just had hard walls and it had a hard floor, and it sounded like crap. And as soon as we put a carpet in there and did a couple other things, then all of a sudden it started sounding good again. So the best thing you can do if you were asking the question is make sure your room is right for the volume and the size and for what you're trying to do with it. So,
and if I can just maybe add one thing, there is no one size fits all kind of a solution
That's right.
for these.
No, there is not.
Yeah, that's right. There's not.
There is not.
A lot of people tend to ask questions like, okay, is there a recipe for absorption, diffusion? I would say that there isn't. There isn't.
There isn't.
Please go.
I'm going to go on about Ron described the edge effect and diffraction and whatnot. And this is what I'm doing lately in many of my rooms and in home theaters as well, is I will put absorption, then diffraction, then absorption, diffraction. And quite often, and behind the diffraction, I'll put a membrane type of bass trap for bass. And what we found is that the absorption of the unit next to the diffraction kind of covers a little bit of that diffraction and expands the absorption over, and so you get the best of both worlds. And the diffraction grading is absorption, so it's marvelous. But the diffraction also gives you a sense of a wall or of a room. It's not like deadness there.
Yes.
Yeah, let me explain something real fast, if you don't mind. Okay. The Applied Physics Laboratory up in Washington, University of Washington, came to visit me one day, and we were talking about a panel that I was testing that many of you are familiar with. It's called a binary amplitude diffuser, a BAD panel. Mm-hmm. Okay, if you go to the manufacturer, they'll say, well, it's a good diffuser. Well, we measured it for diffusion. It had absolutely no diffusion of any kind. It was just a specular reflector that had what we called targeted absorption. So it allowed high frequencies to go through, didn't allow low frequency to go through. It was kind of like a band pass filter is what it was. Yeah. So in this situation, but what we did is we went a little farther into this testing, and what we discovered was something that was interesting. Yes, it was a specular reflector, but the holes did affect the phase when you from about 12K up. So if you had from 12K up to 16K, it changed the phase dramatically. So when you had just the BAD panel only, you had, it's a flat panel only. You had all the reflections were in phase and therefore coherent. Okay, but as soon as you went to the BAD panel, that scrambled the phase up to 700 degrees at a time, and in doing so, it created a balloon that looked like a sea urchin. And I was pointing this out during a tour of the people from the APL, and one of the professors piped up and said, "Well, yeah, we know that from your hearing, because their job is bioacoustics and hearing and how your ear hears." He says, "We know that if you scramble the phase in both ears by huge amounts, like 700 degrees, 800 degrees, it makes your brain think that the room is opening up. It has more of a feeling of spaciousness." And I sat there and I went, huh. And he said, "But think about this." He said, "How many of you are familiar with a Fender amplifier?" And there's a control on a Fender amplifier for guitars. It says presence. And if you turn it up, it makes the Fender sound more open for the guitar. It makes it have a little bit of a reverberation to it almost. And what that was adding 16K noise to the signal. That's all it did. It just added a little bit of noise. There was also a mixing board, Mackie, here in the United States, that had something called an air effect. And what that did is it added low frequency, it added a high frequency hiss to the sound at 16K, which is basically adding the spaciousness to the room. So does it work as a diffuser? No. But what it does do is it does change the phase. So it's a phase grading is what it is. And in doing so, it makes the room sound bigger. So keep that. Yeah, it gives you spaciousness to it. And that was not what they told you it would do, but the facts are that's what it does do, and it works.
Yeah. Good.
It just doesn't work the way they say it does. That's all.
That's what we're finding out all the time. These things work, but they not like they said they would. It's like I was talking about. Somebody posted something about they did these wave guides wrapped in the fiber and hanging and stuff like that. And I said, yeah, I used to do those. They don't work like they say they did, and I think they're more or less quarter wave traps. Basically, the whole area becomes a quarter wave trap.
Yeah, in your chat, there's some technology is more of a scatter plate BAD. It doesn't bring up reflections. There's no difference in the reflections. It's just like all it is basically a flat plate reflector. Okay, mm-hmm. All it's doing is changing and playing around with the variations between the soft spots, the little dots, and the hard surface, and it's scrambling the phase between those areas, those edges.
It's not scattering, it's a phase change.
Right.
That's what it's doing. It's doing a phase change.
Right. So the absorptive part.
High frequency. Yeah, I'm reading this. I'm sorry, Ron. Go ahead. You tell him.
Yeah, it's not a high frequency scatter. That's you're making the assumption that we're scattering sound. That's not what's happening. All we're doing is changing the phase of the sound. And that's not the same thing.
Yes.
Okay, so your ear hears the change in phase as a spaciousness.
So
okay,
John,
but it has
in designing rooms, especially for home theaters and stuff, how important is acoustic isolation compared to acoustic treatment? And when you do acoustic treatment, how important is symmetry?
Symmetry left and right is very important.
Like suppose you've got windows on one side.
Isolation.
If you've got like glass on one side, what happens to the other wall? I mean, that kind of symmetry is what I'm talking about.
You don't want a reflection on both sides. That's for sure.
Right. Yeah.
If you have one side that's reflective, as long as it's not hitting the listener, as long as it's not pointed at the listener, I'd say you're fine. As long as you have fairly even treatment, yes. But isolation is just as important as the acoustic treatment, because if you're waking up the baby with your movie, that's no good. If you're bothering the neighbors and the cops are knocking on your door, that's no good. If you're recording and you're trying to get through this passage and people are banging on your door. Hey, or you're trying to record and your neighbor starts up the lawnmower and it messes up you got to have isolation. You need good isolation. This is one of the first things you want to think of it. This is the foundation of a good room, no matter what you're going to use it for. The foundation of a good room is its isolation from the rest of the house, the rest of the building, the rest of the world. But too often DIYers assume that, I need this, this, and this, and they will throw everything but the kitchen sink at it, and it's too much, or what they've done isn't done right. And it's not as I say, it's not what you use, it's how you use it,
That's
so.
John, Mazman, one second. John, I'll just add one point, John. More often than not, isolation is, I think, a post-mortem kind of a scenario wherein people realize it too late. And the cost of
post-mortem is rather appropriate. It's like, he's dead. Well, I might as well cut him up and see what killed him,
So, the cost of post-mortem isolation is probably going to be more costlier than the equipment put together. It can be such a massive.
I answer so many emails about this, and I have some. I feel sad and sorrowful and hurt when I have people come to me. Well, I built this and this and this, and should I add another layer? No, you need to tear it all out, and I'll show you what to do, because that's really what has to happen.
So the question is, how much isolation is enough? Many times clients say, can we get away with doing just a little bit? We don't want full isolation. We just want a little bit. Let's do just one wall and let's.
How do you listen to your movies? What's the frequency response and range and third octave bands? Give me a chart, and then I'll calculate what you need to stop that from bothering the person sleeping in the next room, or the other way around. Do you live near very noisy things and you're trying to record a quiet instrument? Well, I need to know how the noise is outside. So we do an environmental test. You usually call in a local acoustician to get out his kit. Here, I've got this thing here. It's lab calibrated, and I've got 3 Earthwork mics here that I use to measure. And my system is laboratory grade calibrated. I got the mic calibrator sitting right here. Anyway, they come in and they do a measurement and test and pick and do a noise test, and then print out a chart or send the data to me, and then I'll do my best to calculate. Another thing, Ron and I were discussing this before. I use Insul from Marshall Day Acoustics to predict what soundproofing, how much soundproofing this will do or that will do and stuff. And I'll put these things up, and man, it'll give me like figures of 104 decibels at 6K. And I think that's ridiculous, and Ron's got a face palm right now. And it's true. You're not going to get as much as you think. And even when you look in groups and stuff, well, I tested this and we got this much. Did you test it right? And more often than not, it's less than what you thought.
Yeah, and it's plus what you get in a laboratory is always more than what you would get in real life, because you have all these flanking paths.
Absolutely. This is something I mentioned on somebody's talking about. What if we just do the area below? I had a client in Portugal wanted to do he's got an apartment below that's talking and making noise coming into his room. I said, man, we didn't do a floating floor because you don't have the space. Your floor can't handle the weight. Just don't do it. You'll have to deal with that. And he says, can I just cover the bottom part of that area of the ceiling and isolate that? I said, nope, you got to do the whole thing. And then you're still limited to flanking paths because you didn't isolate that room completely. It's
there's I'm trying to follow along with the meeting chat here. A couple things real fast. Norm Varney's here, by the way. And Norm made the comment about noise control before you can get sound quality, and that's true. If you don't isolate your room correctly, it doesn't matter what you do to make the room sound good.
Right.
So that's something to keep track. Now, Afsona said something about what NRC would be a bad plate measure for a BAD panel. Well, number one, BAD panel measures at about 16K, which is out of the range of NRC. So forget NRC. NRC is a useless number. Okay, you want to know what the
125 to 4K NRC.
Yeah, and the whole point here is it's useless for the usage that we're doing here. NRC is for architects who don't know what the hell they're doing. Okay. Yeah, I mean, like I said, at 77 years old, I don't care what people think about me. That's a fact. It's a useless number that's used for people who don't know what they're doing, so they can pick an idea of what this thing will do. But the facts are, you need to know what the spectrum is that you're doing this in, and you could have the same NRC number and have completely two different materials that do completely different things. So don't get into this trap of single numbers. It's the same way with STC, by the way, too.
Yes.
Look at the transmission velocities frequency, because you may need a lot of treatment at, say, 30 and 40 and 50 and 60 hertz that will never show up on the STC.
Yes.
Right.
Okay, so keep this in mind that there is no NRC at the bad plate to measure at. So you can forget that doesn't exist. And when somebody wanted to know about the waveguide hangers had an effect, John, I would let you deal with that one. Okay, so simple facts are
The answer is no.
Yeah.
Like they'll work however much space they're taking up, however much that enclosure that they're in, measure the depth, quarter wave trap. There you go. That's about
Yeah.
it. I think you'd be better off with 4 inches of 706.
Yeah, I think so too.
Yeah. We
Or-
tried
or-
a lot of things, man. I honestly, through the years, acousticians have tried this and tried that. We come up with ideas all the time. We come up with this idea and we try this and try that. And you know what? Most of our ideas are just wrong.
Yeah.
And you got to face it. And when I've said, oh, that dense stuff will reflect bass, and that's according to the formulas that I had.
Yep.
And I was doing the same thing. I was talking to a fellow who worked out a program. He's a really smart guy, good guy, and he's really set on these formulas that he's using, and he's modeling this stuff, and it doesn't actually work like that. And he'll argue with me. And I said, and so I'm having a conversation, and I'm telling him, you can't really trust the formulas. You got to test it, and then I go back to my group and I'm talking to the guy. Well, according to the calculations, this is going to reflect. See, I'm doing the same thing. I'm doing it again.
Yeah.
We assume too much. We acoustics is counterintuitive, and then I go to intuit what it's going to do. No.
Yeah. One of the things I find interesting here is there are people out there who believe the simulations are the end all and be all.
Oh my
Okay.
God.
And I have to explain to them, please understand, the simulation you got is derived from some measured data at some point.
Yes.
So the measured data comes first, then comes the simulation. And then sometimes you may find that the measurement was not adequate. Therefore, when you do get an adequate measurement, then you have to change the simulation.
Yep.
And I've been arguing with people for a couple of years now. They're saying, well, the simulation is more accurate than the data is, and I'm looking at it like, what world did you just come from?
Yeah, right. Yeah, it's the only way. Empirical evidence, empirical data, something you can hold in your hand, something you can see and test. That's what we need. And
absolutely,
as Ron said before, garbage in, garbage out. The computer will only do what it's told.
So, John, what's the best shape of a room for a home theater? Which is the best kind of shape?
Rectangular cuboid.
Yep, I gotta agree with him.
And when people start to splay walls and have,
Ron, do you agree with me? A rectangular cuboid?
Yeah, it's the most predictable and the easiest street to make well. Anything that you have that's above 4 sides is going to give you some kind of convex shape at some point.
Yes.
And that means it's going to focus the sound at some point. Okay.
Right.
So You know, if I were trying to do something and I didn't want a cuboid, I would make sure that whatever flat surfaces are used for that room are all convex shaped back into the center.
Right.
Okay. I produced through a friend of mine named Jim DeGrandis a bunch of simulations of diffusers. Jim is probably the most advanced guy in the industry right now as far as designing diffusers, and he's come up with a way of predicting what's going to happen with the shape of something and then seeing what happens. He's actually put these things into room areas where you can actually see the room frequencies and sound fields develop in the room over a period of less than a half a second.
Nice.
You know, and if you're interested at some point, I have them. I'll be happy to share with anybody who's interested. But these at least give you something to think about, because none of it matches up with what you think is going to happen.
Yeah.
And I think that's the key behind the whole thing. And again, everybody has their own taste. Some people like quadratic diffusers on the side wall, the rear wall type like things. Some people don't. That is taste. That is not necessarily tied to quote science. Okay. What we've found over the years is that if you use a quadratic, you're going to be changing phase. If you change phase, you're going to lose localization. Okay, so if localization is important to you and your sound field that you're trying to record has, bass on this kind of corner, and you have the piano over this corner, and you have the drums in between and stuff, then having a stage that has localization of individual sounds becomes very important. If that is the case, then most of the diffusers you want to use are what we would call geometric diffusers. So things like barrels, or curved surfaces, triangular surfaces, round surfaces, spheres, sections of spheres. Okay, these are all shaped.
Ron, are you saying that things which are not essentially going to change the face of the face? Is that right?
Yes. Yeah, these things are geometric, and what they are is they work on specular reflections. And if they're specular reflections, they don't change the phase.
Right.
Exactly.
Yeah, okay, let me back off. They change the phase, but in the same way that a specular reflection will.
Yes.
Okay, which changes based upon runtime.
Yes.
Okay, but it doesn't change it because of the reflection. If you have a QRD, you're going to do a phase change because of the phase grading. Okay, so if you want to maintain localization, then you treat your sidewalls or your ceiling or whatever with geometric type reflections, which which are basically reflectors. They're not diffusers. Right. And one of the things I want to make really clear, and I think John will start to understand what I'm saying, because I think he's working with this too, is the rest of physics thinks that acoustics is a junk science.
Or art.
Yeah, or an art, okay? Because we refuse to accept that the other parts of physics have a place, and they describe things. And there's words that are used in physics that are common, but we refuse to accept those in acoustics for some reason. We redescribe all these things, like the word diffusion. Okay, we're using diffusion for all these units that diffuse, quote, diffuse sound, right?
But they don't.
But in reality, what diffusion is when some kind of energy goes through something. Yes. So if you have water that is muddy and the particles diffuse the sound or diffuse the light, so it becomes kind of glowing instead. That's diffusion. So the light goes through the element and comes out the other side different. Okay, so we have items here in acoustics called acoustic couplers. And you'll see these things look like egg crates with no backs on them and stuff, and it just looks like an egg crate with no back or front. Okay, those are acoustic couplers. What they're used for is to take random sound and make it all come out the back in the same direction, and basically in a coherent method.
Right.
Okay, and you can see that when you have a fluorescent light fixture that has an egg crate on the front of it. If you look at the light from the side, the light will seem to have dimmed by about 40-50%, because you can't see the light until you're under it. When you're under it, all of a sudden it's bright. It's like, wow, okay, where'd that come from? Okay, but if you're off to the sides, you don't get that. You don't get that in your eyes anymore. So that's what a diffuser is. So all these things we call diffusers, like QRDs or any of these other things, those are in fact diffractors, not diffusers.
Right.
They diffract the sound, or they are what we call reflector. I think it's we call them reflectors. Yeah, they're
polys and geometric shapes are reflectors.
Right.
What is normally called a diffuser are basically diffraction devices, and some of them are plain diffraction, and others are phase change diffractors.
Yeah.
Right. Yep. And that's basically what it is. So when I hear people telling me about their diffusers, I'm looking at them going, oh, are they like acoustic couplers? You put sound on one side and comes out the other side, kind of like a grill on an organ chamber. Okay, you have all the speakers inside the organ chamber or the pipes, and you have the grill going out, into the room, and they're usually some kind of grid work of some kind. And those are diffusers. That's what they're intended to do. But that's the other thing is the effective range of all these things. If you want to use a coupler in front of an absorber, the question is, how far in front of the absorber should it be? And what we're finding out is a maximum of 1 to 1.5 inches. That's it. You don't want to have it 2 feet down below or a foot below, because what happens is it gets too big. Now the edges on the far side will start to diffract, and it will not keep everything going in the same direction. So you're going to have phase changes occur in that situation, and that's not good. Okay, so I think, John, you can talk about these panels on the walls and how far off the walls they should be and all the rest of the stuff. So I'm gonna back out of here. Okay.
Oh, panels on the walls. Now this is an interesting topic and a subject of much discussion. There's a whole lot of people, and there are names in the business that talk about, you want to take your GIK or whatever manufactured panels, or ones that you make yourself, say they're this thick, and you hang them off the wall on little pegs so that there's a gap behind them, and they say that it increases the absorption. In fact, in testing, what do they call it, Ron? I'm sorry, I'm really foggy right now for some reason. It's 11 o'clock.
If it's a panel that's off the wall and there's no surround around it, it's an open back area. It's either a B or C mount.
B or C mount.
Yeah.
And compared to B mount and A mount, which is the sides are covered and it's closed to the surface where it's being tested on, wherever
that's right on the surface.
If it's got air behind it or not, it's closed.
Yeah.
The same product, say for instance, you got a B mount with that space, say it's a 2-inch product with 2 inches of space. You do the same test in A mount, and you're going to have a shift in the knee point. Say you look at a high pass filter. Okay, you got the low frequency coming up, and then it's got that knee, and then it's flat all the way up past that. So you got this curve here. The knee point is here. So when you raise add an air gap and you close the sides, what it does, it shifts the knee point lower in frequency. Right. What people have DIY tested, they'll notice a slight increase in the 1-2 kilohertz absorption at that. Yeah. So what is that? I mean, how does that help really?
Well, the big thing here is if you go on the internet, they'll tell you, well, if you have a 4-inch panel, you should put a 4-inch gap behind it.
Right.
Okay. That's, and this is, quote, knowledgeable by everybody out there knows this. Okay. If you actually test this idea, what you're going to find out is this. If you have an open edge and the air goes through this thing, it forms a compression area behind the panel. And when you compress something, if there's no surrounding around the edges, whatever is compressed will flow to the outside edges and out. Okay, it's like, like having a drum head. You push on it, the air will go down and it'll go out and spread out. Okay, and if the edges are open, it will spread out at a certain rate. So if the pressure is more than the amount of outflow, then you'll get an increase in absorption, because what it does is act like a piston. Okay, now as soon as you open up that edge to more than 1 inch, then the outflow equals the pressure or more. So therefore, there will not be that piston effect, and therefore you will not get an increase in low frequency.
There you go.
And that's how that works. So if you want to increase the low frequency, you then extend the surrounding all the way down to the surface. So you have a captured chamber of air behind the panel that is sealed to the wall.
Yes.
And that will make
it doesn't have to be glued. It just touches the wall. That's all you got to do.
Yeah.
Wall or ceiling or floor, wherever you're putting it. That's the partition, the boundary. Yes.
So what it does is it stops the outflow. It makes a compression seal, just like you would for a shock absorber in a car.
Yeah.
So now you can increase that space behind, and you'll get an increase in absorption depending on the space by increasing the space as well, because you're making this chamber different frequencies depending upon how the compression goes. So yeah, if you want to increase a low frequency response, make an E mount, which is the surround goes all the way from the surface of the unit all the way to the whatever it's attached to.
Indeed. Yes.
John, I think we have. I for your benefit, I think we need to probably draw a hard stop somewhere. I think it's already 11. Yeah, it's already 11.
Yeah, where Ron is, it's his morning. Here, it's 11.
Yeah.
It's after 11 p.m. and
it's 11:15 for you. So I think Mazban and we are going to maybe take one last question, which is posted in the chat window. John, all I can say is that I think we will require you and Ron to come back for another session, maybe at a future date of your convenience, because the topics are so vast, and I think I don't even think we have touched the tip of the iceberg.
We've not even started the design of the room.
Oh, we're just looking at the So I see a bit of ice on top of the water there.
Yeah, it's pretty vast in many ways, and I think a session of this duration will not do justice. So we might have to stagger this in multiple sessions, if it's okay with you, the two of you. So given
I was looking at I was looking at your I was looking at your chat. There's a lot of questions there, and I was looking at all those going, oh boy, that's a whole another 2-hour session just answering those questions.
Yeah,
exactly. So I would say that we will take one last question, if you don't mind, Ron and John. Maybe we'll take the question which is posed by E mounting versus C mounting. Is there any difference? Is the question by Evisonus Technology, and if you can, one of you can, if you can answer that question.
Well,
the question
C mounting, B mounting means the border is open to the room. Therefore, the limit is about 1 inch spacing off the wall. After that, it disappears. Okay. E mounting means that the air chamber is captured behind, and therefore you will always get a low frequency increase, because you have captured air, and it will compress and it will not go away.
Similar to a Schroeder diffuser with the well. Okay.
Yeah, we can talk about that later on.
Yeah, we'll talk about that in the next one.
We'll talk about what everybody talks about the Schroeder diffuser and how it absorbs, but the method they use is very different than what you're thinking. It'd be better, I think, in this case, John, if we actually had a diagram where we actually show them that.
Okay. Yeah, good deal.
Yeah, I think that.
Eventually, we'll get into how to design a home theater.
Sorry, John.
Eventually, we'll get there.
So I think Maz, you want to just conclude?
Sure,
with your
sure.
conclusion?
Guys, thank you so much. John and Ron, thank you so much for your valuable time and your fantastic insights into this inexhaustible topic. I mean, we not even
Thank you.
scratched the surface.
Thank
There are
you for
myriad,
joining us
questions.
in our learning experiences. This is really what this is all about.
True.
Yeah.
Ron and I teach, but we have to teach what we're learning. And you know, as well, I remember Yoda said to some who was it? You have to unlearn what you have learned. Kind of what we have to do sometimes.
True.
It's not unlearn something. It is to let go of the things that you thought was right, and you're holding on to. Oh, that doesn't work. You know, kind of thing.
Yeah. Somebody said if you ever want to learn something, try teaching it.
Oh yeah.
Yep.
Yeah, exactly. Yeah, and this
Absolutely.
helps me too. When I talk about it, I go, wait, that's not right.
Yeah. When I first started teaching, I was teaching ease, how to do ease. And the people that came to my class were some really big brain guys that were involved in acoustics. And they kept, you know, and a couple of you might know, but they have a reputation of being guys who love to kind of let you have all the rope you want before they hang you. Okay. And so they let me have my 2 days worth of rope, and then they pulled the rope on me a couple times and asked me questions. It's like, and I find what I learned was if you don't know, it's better to just say, I don't know, but I will find out.
True.
Yes.
Right.
Okay.
That's our word right there. That's what we always say. Well, I don't know.
Yeah.
We'll find
Yeah.
out.
But all I know is I was teaching during the day, and then at 2 o'clock in the morning, I would call Wolfgang Honert and say, Wolfgang, here's a question. What's going on here? Okay. And so that's how I learned initially. Okay. And then I found out that, you know, that it applies to the rest of physics and stuff. And it was like, okay, so as time goes on, I've learned from the best. Okay. Only because what I've learned is in a lot of cases, if you want to learn, just keep your mouth shut and listen to the experts talk.
True. True.
Okay. Yeah. And then the other thing that happens is you get older. Eventually, you know, your body goes, okay, I'm going to learn because I have no other choice. It's kind of like osmosis more than anything else. So,
Yeah.
you know, so I think at this point in time, that's what I think John and I are very much into now is we want to, I'm at the age now where I want to pass on what I have, because to be honest with you, when I die at this point in time, all this knowledge that I've got is going to go away. So unless other people know what we're talking about, then they're going to have to rediscover everything we discovered again. Okay.
Yeah.
And that's what's happened in our industry is we rediscover over and over what other people have already discovered previously, but we've forgotten. So I want to make sure that that this stuff is learned by everybody. And so we want to share it with as many people as possible and hope that somebody will be able to take what our ideas are and continue on and extend them. You know, learn more about them and learn more about this stuff. So, you know, so we're not saying we're the end all and be all, because we're not. Okay. We hope that what our background is such that it will inspire other people to go on beyond what we're doing that are younger than we are.
I think you summarized it as good as it gets, Ron. I think it's very important for us to have an attitude of being a student at all points of time, because being a student always gives us the flexibility of assimilating more. The moment you say that you're an expert, that's probably that's something that
End of learning, I suppose.
Yeah, that's the end of
End of learning. Yeah, let somebody else call you an expert.
exactly.
Yeah.
Exactly.
Yeah. I know that when I started learning all this stuff, I had to go back to, at least it's how I do things. I had to go back to all my students. I have hundreds of students, and I had to go back to them and apologize for having taught them this stuff because it was wrong.
Oh.
But I said, at the time I taught it to you, this is what everybody knew, and I did the best I could. But now that I've learned, you know, I can either ignore all you guys and let you guys go, okay, well, we'll learn it as we go, or I can go back and apologize and say, look, I didn't know any better, but this is what I know now. If you want to follow me and some more, that's fine. If not, that's fine too.
Right.
You know, but you have to be able to go to other people and say, look, I was wrong.
Right.
And if you can't do that, you can't teach.
that requires a lot of balls. You require a lot of balls for doing that.
Yeah, it requires a lot of courage, actually.
Yep.
It's really about, it's a kind of a life philosophy. If you have the courage to be honest and to help people, it's what I always say, do what you love, go out and help people, surround yourself with people who are productive and positive and encouraging. It doesn't mean you can't criticize from time to time. No, that's wrong. No, don't do that. That kind of thing. That's fine. But surround yourself with people who are more knowledgeable and better at what you do, rather than surround yourself with a lot of sycophants, and whatnot, and admit when you're wrong and move on and keep moving, it's important. I think it's sadly lacking in a lot of this in this industry. There's a lot of folks, it's hard for them to say, oh yeah, I was wrong about that. Okay. Yeah, let's do this. Let's move forward. It's actually not as hard as you think to say I was wrong, and you just do it and move on. It's like the plumber who goes to the lady and says, my diamond ring's down the toilet. Oh, really? And she just reaches down there and pulls it out, washes it off, hands it to her, goes wash his hands. Done. That's really all it is. All there is to it is, don't let pride or whatever block you, because
Take my word for it. John, when I first met John, about 2 years ago, year and a half, 2 years ago.
I think it's more than that, but yeah.
It's hard to remember anymore. But when I first met him, I didn't agree with 99% of what he had to say. Okay, so I came into his room and my first thought was, John, you're wrong. You're wrong. I'm sorry. You're wrong. I'm wrong. Okay, and he and I had some very interesting tussles for quite a while, until I showed him. I says, well, here's what the actual measurement says, and he looked at it. And he says, I never saw that before. Okay, John he swallowed his pride more often than anybody I know, in order to be able to say, look, when you show me I'm wrong, I'm willing to change my mind. Now, take people that know me know that I am very, very hard to get my mind to change. But let me tell you, people who know me also know that you give me a reason to change my mind, I will change and gladly go off in another direction. Okay.
Yeah.
But you better be able to prove to me why I'm wrong.
Right.
Okay. But I will definitely change. And that's what I like about John, is John was interested in changing. And when I looked at this stuff with absorption, my first thought is I was taught absorption is the absorption divided by absorption coefficient is divided by the area. I taught that. I believed it thoroughly. I thought that was the only way to go. But when I was able to see that it didn't make mathematical sense, then it was like, why not? And then that's where we started all this stuff. So you got to be open to the idea that, everything that we believe in, what we call the shibboleths, okay, could be completely wrong.
Right.
And you need to be open to that idea that everything that we thought we knew, we don't know. and we need to learn a whole different way of looking at things. And that can be scary, because that takes away all your moorings.
Right.
It's like being on the open ocean instead of being a harbor.
Yes.
And you got to be willing to get on that ocean and possibly sink. But that's what I like about John, is he's been able to look at what we do, look at why we do it, why we recommend it. He would ask me questions, I would answer the questions to the best of my abilities, and then we would sit there and we come up with an experiment that we get tested. And that's what we're doing right now. I've got piles of equipment that John has sent to me to be tested. So, starting next week, we're going to go back to doing testing again. So you're going to be seeing a whole bunch of stuff come out in the next 2 or 3 weeks on diffusion and absorption, on things that we thought we knew. So all these things with the wood slats and stuff over absorbers, we're actually going to test all that stuff.
At this point, I'm prepared to say, oh, well, that didn't work. Move on. I'm serious. Yeah,
it's one of these things where you have to just set it up there and say, look, let's just put it together, test it, and we'll see what happens. Okay. Right. Because we all have different ideas of how it works. Now let's find out which one actually tests right, or do all of our ideas be wrong? And we have to form a whole nother set of ideas. Okay. Yeah, right. Because, that's one of the nice things about testing is sometimes physics just says, you know what? You have no idea what the hell you're doing. and you might as well completely rearrange your whole thought processes because this is what it is.
So would I be right in saying that probably what we had earlier were postulates, and what you guys are now doing are basically developing new what is the term for that? The difference between postulates and actual theory or something, a law, because postulates are something which are just not.
Let me correct something first. Most people use the word theory as though it's an idea or a hypothesis. In science, it's called, there are hypotheses and there are theories. And a theory is something that is confirmed by evidence and experience and is clearly evident. And it's basically as close to a fact as we get. The theory of gravity, the theory of relativity, the theory of whatever, the gravitation of the, how that works. Those are scientific theories. Now, in layman's term, a theory is just an idea or a hypothesis. A hypothesis is an idea. We come up with ideas all the time. Most of them are wrong. And yeah, so what? Thing is, when you understand that we are mammal primates, we live on a little ball of dust that's hurling through space around a star in a isolated quadrant of a galaxy that nobody knows about, nobody cares about, and it makes you humble. You go, wait a minute, we're just, so we do the best we can with what we've got. I was talking to a client the other week. I said, in the past, I've done this and I've done this and I've done this, and I followed my mentors and I did this because they did it and I took their word for it. And then tested it. No, that doesn't work the way they thought it did. And I've even gone, with Ron's latest work, acoustic absorbers and diffusers by the renowned, D'Antonio and Cox. They're great. They really know their stuff. They really do. But what they tested didn't match what they claimed to. Yeah, I don't know. It just doesn't work the way they thought.
Yeah, it had to do with scale modeling versus full scale.
Yes.
Sometimes scale modeling does not equal the same thing as full scale.
Same way that ease doesn't work well with small room acoustics.
That's right.
It's because it's the model size. So yeah.
Right.
Yeah.
So you have to know what your tools are. You have to know how to use your tools.
Yeah.
And then you have to know what the limitations of
you need to know the limit. Exactly. You need to know the limitations of the tool. True.
Yeah.
Very true.
Yeah, everything has limitations.
I think, yes.
Yeah, where's the tool?
Yes.
I had a tool here. Oh, here's a tool. Yeah. Limitation of this tool. You don't put screws in with it, although you can, if you, but no.
Tell my wife about that.
You can probably get away with putting nails in this, but no, don't do that.
That's a nice tool behind you, though, for acoustic purposes.
Yes, this is my dodecahedron. I've got a couple of them here. This I built, and it's a 300-watt unit, capable. It works from about 31 to 16K.
Wow,
not bad. Okay. Not bad.
Yeah, I have something to share with you before you guys go. Talk about the laws of physics and stuff. I was traveling in a state here in the United States called Oklahoma on a freeway, and I got a ticket for doing 75 miles an hour in a 70 zone. The problem was the policeman was on a hill about a mile and a half away at night, and he was telling me that he could see how fast I was going, in spite of the fact we were both going in the same direction. So I'm not going across. I was going parallel to him at the same time, and I'm going at that distance, that time. You can't see the differential speed. And we're talking about physics here. And I was in court, and I brought up that I'm a physicist, and this is what's happening, and this is what it is. And the prosecutor came back, and he said, Mr. Sauro, he said, there are theories of physics. There are no laws of physics. He said, the only laws that we recognize are the ones that come from our legislature. And I pointed out to him, I said, well, if that's the case, then we should go up to the second floor and have you step out of the window and see if we can EQ the law of gravity. Because if that's only a theory, you probably won't hit the ground. But I said, I'm willing to bet that you'll probably become a grease spot on the ground first.
True.
I said, so just please tell me about the law of gravity versus the theory of gravity. Good one. Yeah, I'm sorry, but John and I see this all the time, and I'm sorry, but if this hurts somebody's feelings or not, I don't care anymore. There is ignorance. Ignorance can be fixed by education.
For most, ignorance is bliss. But yeah.
Well, yeah, but you can fix it with education. You can educate somebody to get them out of ignorance.
It's
Problem
okay
is,
to be ignorant, but we're all of us are ignorant about many things.
But there is something called stupidity.
Yes.
Stupidity is permanent.
Yes.
It doesn't go away. Okay. So, and the problem is there's more and more stupidity in the world than there is ignorance.
True.
So if you guys have never seen the movie, there's a movie out there called what is it? Jim. Idiocracy. The name of the movie is called Idiocracy. And I looked at the first time my wife asked me to see it. I looked at it. I thought, oh, bunch of bullshit. Okay. I have now become a believer in the movie Idiocracy. The world is becoming more idiot. It's definitely the same. And it's scary because at my age, I'm sitting here going, okay, maybe dying is not such a bad thing because I won't have to go through all that stuff. But if you ever get a chance, see the movie. It's called Idiocracy. I think it's what's his name? The comedian. I can't remember. I can see his. Jim Carrey. Yeah, Jim Carrey. Right. Yeah. And so it's a good movie. You have to see it, but it definitely makes you think that perhaps the world is going in the wrong direction sometimes.
Does it have 25 hertz content?
Yeah, right. Probably. Yeah, it's really something. I mean, if you are a pessimist, this doesn't sound so bad after all, but it definitely makes you think that maybe the world is going in the wrong direction. So I was, when I saw that, my first thought was, oh God, we can't be going that way. We really can't be becoming that stupid. And then I look at what's happening in the world, and I'm realizing that's exactly what's happening.
Yeah, that's a lot what Jim Carrey really wants to say about the world. His comedy has always reflected his viewpoint on society, and it's pretty smart, but it's to wake you up, really. It's to make you think, oh, wait a minute, I don't want to do that.
Yeah, that's so all I can tell you is that we're just trying to educate. That's all we're trying to do, and the best we can do is hope that the people who are we can help them. I'm sorry, but I've learned after a while you can't fix stupid. Okay, so all you can do is just talk, and people either accept it or they don't. If they don't, and this is what facts are, this is life.
I've always described.
You would say it's their loss. If you would say that it's their loss of not being able to accept reality.
Well, accepting reality. I've got architects. I've got people that are engineers telling me they want to build an airplane with no wings.
Oh God.
But we need to do this because this is what we want. And I'm looking at him going, I don't really care what you want because you're never going to get what you want because Mother Nature gets in the way.
You know,
And
you
it's
could,
like,
as Meredith Baxter said in one movie, I think it was Grumpy Old Men. He says, well, you can wish in one hand and crap in the other and see which one gets full first. You know,
yeah,
But-
that's a good one. I like that one.
yeah,
Yeah.
yeah.
And I experience a lot of times in church. Okay. I have pastors who come to me and say, I don't want to put that speaker up there because it blocks the view of our beautiful window.
Mhm.
And I'm looking at them going, that's the only place that speaker can go and work. And they go, well, can't you EQ that? Well, if I could EQ that, I would EQ gravity so that you wouldn't fall. You know, but you know, you go ahead and do whatever you want. Here's the EQ, go for it. Okay. But
Yeah.
it's not going to change the fact that physics says this is where it goes, like it or not.
Church acoustics is another whole ball game altogether, if you ask me. Sound systems and acoustics in churches, especially
Yeah.
the old ones.
Oh yeah, well, John Davis, who just passed away a few weeks ago, is kind of the guru of sound system design here. He put together a group called SnotCon. Yeah, so he put that all together and stuff. And in SnotCon, he had a saying one time. He said, "If bad sound were fatal,
Yeah.
90% of the churches would be dead."
Yes.
Oh, okay.
And it's true. I mean, some of the sound systems are so bad. It's like, okay, yeah, we have somebody in the church who has a great stereo system, and therefore he can design a good PA system. And it's like, well, what's the difference? Big difference. Okay, but the facts are they don't recognize that sound to sound to sound to sound. Doesn't matter whether it's a whole different field or not. You know, so the you know, there's an old saying in churches, you go through 3 sound systems. One of them is somebody locally, okay, or in the case of in this case, it is a guy at the music store who sells speakers. Okay, and he will sell you speakers. Say, how many people do you have in your church? I have 200 people in my church. You're going to need 200 watts of power to drive it. 1 watt per butt. Okay, and then you find out this guy has now gone on to work with a different music store, and he now designs by the old case of yes, but okay. So he designs and puts it up there, and he will say yes, but this is designed because we now have more knowledge, and it will not work, and the whole thing. And then they'll do, you know, finally computer aided design, you know, and they'll do their third system. It's always the third system works really good because they finally actually hire somebody who knows what they're doing. But it takes 3 systems to get to that point every single time, you know, and that's because people try to save money and try to hire people to do that. So, you know, it's like
ends up costing them far more
Yes.
Yeah.
than it would have.
same way with acoustics,
just
by
to
the way.
do it right.
Yeah, if you build the acoustics in while you're building the room before you even design it,
I
it will
think
cost you.
I think this. I think the adage "penny wise, pound foolish" is very apt out here in our industry.
Yeah,
Yeah.
It costs 5 times as much to retrofit the sound acoustics than it would be to build it in when you build the building.
Absolutely.
True.
Yeah,
Very
5
true.
times. You know,
Yeah.
so I know there was a question that came up in the meeting chat about when do you start designing? You start designing before you ever put pen to paper and make a design of a building.
Yeah,
That's when you start designing. You know, and if you do
The
that, put
unfortunate-
it in.
The unfortunate part, Ron, is that we often end up entering the project very late into the project, and that's something I think there isn't enough awareness in the industry about the importance of that room acoustics plays, or let's say soundproofing plays into the entire design of any space. So I think the awareness needs to be improved, and guys like you, guys like Norman, I think need to play a very important role in getting that awareness up. And talk to the various associations that exist globally.
Yeah,
I think
we've been doing that for 40 years, and so far it hasn't made too much of a difference. So
Especially
it's
the
like,
architects associations. Those
Yeah.
guys.
Most people think that we're just trying to get work.
Yeah.
And I you know, I post many guys. I've got a stack of clients here that I'm backed up. I've got like 40 clients I need to finish, and I don't need more work. I mean,
Right.
I'll take it. I'll just put you on the pile and we'll get it done. But it's not why I post these things. It's not why I talk about you need to hire somebody who knows what the fuck they're doing. Excuse
Right.
my language. If
Right.
anybody's
So anyway, guys,
sensitive.
thanks. That was a really informative session. It's really gone over time. It's
Yes.
it's,
Sorry about that.
10 out here. No, but it's brilliant. I mean, we're just enjoying this lovely session. I mean, we lost quite a few of our participants, and I think
Lost them.
time to say good night and God bless, and let's do this again sometime.
We'll have you
Okay.
guys.
Yeah.
We'll
Thank you,
have you
Mark.
guys again in the future, and I look forward to that. It's been a great session. Thanks, thanks,
Very
Ron,
well.
John. Thanks, Mazban.
Thanks, guys.
Thanks to everyone who has attended and for the lovely questions that you guys have asked.
There's,
We'll
Yes.
there's
see
a question saying, where can I find the link for the next meetup? We'll
It'll be-
definitely keep you posted when we get your time and when you guys are free and when you're willing to do another session. We'll keep everyone posted.
No problem. We look forward to it.
Thank
Looking
you.
forward to it. Thank you
Thank
so much.
Have
All
a
right,
great
thank you very much.
Have a
night. Have a great night, John. Have a great day, Ron.
Okay.
Thank you.
Yes,
Okay.
no problem. I'm gonna go watch hockey now. See you later, okay?
Always
Okay.
wonderful to talk with you, Ron. And
All right, take care, guys.
see
Okay.
you soon. Okay.
Bye.
Okay, bye.
Bye.
Bye. Bye, everybody.